Okay, it seems like it started, right? Can you confirm?
John says it's live now.
Okay, great. Okay, let's get started now then. Well, welcome everyone. This is the last lecture of our computer architecture class of fall 2021. And this time we're going to end up with cutting edge research talks. This is the third edition of the cutting edge research talks that we're doing this semester. And I think this is a great way of ending the semester. We've covered a lot of advanced topics in this course, and we've seen a lot of research papers, and we've seen 7 of them presented in the past research sessions. And today we're going to see 4 more of them. And we're going to start with Ataberk Olgun, who is going to present QUAC-TRNG, which is a new method of generating true random numbers using analog operational properties of real DRAM chips. And Ataberk was an intern at Safari for some time. It's been some time now, I think. And now he's finished his master's degree in Turkey, in Ankara, and he's going to join Safari as a PhD student very soon, in less than 20 days, hopefully, if everything works out. And hopefully it'll work out. And this paper was published at ISCA this year in June. So it's the cutting edge in random number generation in DRAM. So Ataberk, please go ahead.
Yeah, thanks, Onur, for the introduction. So I'll skip this slide because you already know the title and where it was published, and just go with the summary. So DRAM-based true random number generators can provide low cost to random number generation to a wide variety of computing systems. However, prior DRAM-based TRNGs cannot provide low latency and high throughput to random number generation because these TRNGs either sample fundamentally slow physical processes, or they cannot effectively harness entropy from DRAM rows. Our goal in this work is to develop a high throughput and a low latency TRNG that can be implemented using commodity DRAM devices. We make the key observation that a carefully engineered sequence of DRAM commands can activate 4 DRAM rows in quick succession. And we call this new phenomena quadruple activation, and we refer to it as QUAC for short. Our key idea is to use these operations to simultaneously activate DRAM rows that contain conflicting data to generate true random numbers on DRAM sense amplifiers. We develop QUAC-TRNG, which repeatedly performs these QUAC operations and post-processes the results using cryptographic hash functions to generate true random numbers at high throughput and with low latency. We evaluate QUAC-TRNG throughput and quality using 136 real DDR4 chips from 17 DRAM modules. Now, our results show that QUAC-TRNG can achieve up to 5.4 gigabits per second throughput per DRAM channel, outperforming the state-of-the-art by 15 times for their base and 1.4 times for their throughput optimized configurations. So QUAC-TRNG generates true random numbers with very low latency. And finally, we use standard randomness tests developed by the National Institute of Standards and Technology to measure the quality of QUAC-TRNG, and we show that QUAC-TRNG is a high-quality true random number generator. And here's an outline of this talk. I'll briefly introduce true random number generation and then discuss why we need DRAM-based true random number generation in our current computing systems. So there are many ways to define randomness and also what makes a random number random. And for simplicity, we will go with this definition here, a sequence of bits without any discernible pattern. As an example, you can probably notice that the first 2 bit streams presented here in red color look less random because the bits that make up the numbers follow a pattern that can be identified. However, the 3rd bit stream does not seem to follow a pattern, and therefore we could say that it's random. To produce these random numbers, we use what's called a random number generator. A random number generator outputs random numbers, and this can be a device or a program running on a computer. To see how RNGs generate random numbers, we will briefly look at 2 categories of random number generators. So pseudo-random number generators continuously perform arithmetic operations on an initial value called the seed and maintain a state and output a random number based on this state. Two random number generators sample random physical processes to generate random numbers. Now, since PRNG output depends on this initial seed, someone with malicious intent could fully regenerate the stream, the full stream of random numbers. And this is not the case for a TRNG, as it's not possible to regenerate the output of the random number generator by observing the physical process. So if we were to observe the physical process, we would get a new random number. And from a cryptography perspective, this makes TRNGs more secure compared to PRNGs. One important characteristic of a true random number generator is its quality. And we need a way to measure the quality of a TRNG to systematically distinguish between good and bad TRNGs. And a common way to do that is to conduct statistical testing on TRNG outputs. And these tests analyze the random bit streams and evaluate a number of their statistical properties, essentially, to find patterns. Typically, the test will either fail or pass, depending on how well some statistical properties are satisfied by this random number sequence. And to summarize, the idea behind TRNG quality assessment is to make sure, as much as we can, the output bit streams cannot be identified, does not contain any patterns that can be identified by computers. And we call TRNGs that produce such bit streams high quality. These high quality random numbers are critical to many applications. Some examples are cryptography, to generate cryptographic keys and signatures, in scientific simulations to provide Monte Carlo methods with numbers that well fit a distribution, and even in machine learning to perform randomized training on neural networks and in genetic algorithms. True random numbers can only be obtained by sampling random physical processes. And unfortunately, not all computing systems are equipped with this dedicated TRNG hardware, such as low power embedded systems and commercial processing and memory systems. And this greatly limits the application space supported by these systems. And it also weakens the security guarantees provided by these systems. DRAM is widely used as main memory in a wide range of computing systems. And TRNGs based on DRAM enable true random number generation within DRAM chips. This is particularly useful for supporting true random number generation in constrained systems, as they can be implemented with low hardware cost. And DRAM-based TRNGs also provide high throughput, which can open the application space in computing systems that lack the dedicated TRNG hardware. Finally, DRAM-based TRNGs are synergistic with processing in memory systems. These systems typically perform computation directly within a memory chip, which improves the overall system performance by avoiding unnecessary data movement. True random number generation within DRAM enables PIM workloads to sample true random numbers directly within the memory chip, and thereby avoiding communication to other possible off-chip TRNG sources, and it enhances the overall security and privacy of PIM systems. Now I'll go over the relevant background on DRAM organization. So a processor's memory controller communicates with a set of DRAM chips within a DRAM module through a memory channel. Each chip contains multiple banks that share a common interface. And DRAM banks are organized into subarrays that consist of a set of word line drivers and sense amplifiers. Subarrays are further partitioned into DRAM mats, which are essentially collections of DRAM cells, and these are separated from each other by word line drivers. Within a DRAM mat, DRAM cells are laid out onto a two-dimensional array of word lines and bit lines. And a row of DRAM cells is essentially a DRAM row. And here's a simplified diagram of a DRAM cell. We will look at how we access this DRAM cell. And this is a diagram showing how a DRAM cell is connected to the sense amplifier. A cell is composed of two components. The capacitor stores data, and the access transistor determines if the cell is being accessed. This transistor is controlled by the word line, which we enable to connect the DRAM cell to its bit line. And the bit line bar is essentially the inverse of the bit line. The DRAM sense amplifier has an enable signal, which determines if the sense amplifier is currently active. Initially, both the access transistor and the sense amplifier are disabled, and both ends of the sense amplifier are maintained at half VDD. In this example, the capacitor is fully charged. And to access the cell, we first enable the word line. This connects the capacitor to its bit line. Since the capacitor has a voltage level higher than the bit line, charge starts flowing from the capacitor to the bit line, resulting in bit line voltage to deviate slightly towards VDD. When we enable the sense amplifier will compare the voltage levels between voltage levels of bit line and bit line bar and amplify the deviation until bit line voltage reaches VDD. Since the capacitor is still connected to the bit line, the amplification process also restores charge in the capacitor. We'll now look at how DRAM operates at the scope of a single subarray. And because memory controllers typically access DRAM cells in the granularity of a cache line, we will, in this figure, we will combine consecutive cells to form cache lines. On the bottom, we have a timeline of DRAM commands. And first, we activate the first row. We send an activate command to copy its cache lines to the sense amplifiers. At this point, we can read data from the sense amplifiers using read commands. To access another row, we must first send a pre-charge command to the DRAM bank to close the open row and pre-charge the bit lines. We can now activate another row before we read data from it. To ensure correct DRAM operation, we must obey certain timing parameters that define intervals between successive DRAM commands. Two important parameters for our work are TRAS and TRP. So first, TRAS is the time required for the change for the charge to become restored in the capacitors, such that we can pre-charge the bank without causing any failures. And TRP is the time it takes for a bit line to become pre-charged to half VDD, such that we can activate a new DRAM row. So successive pre-charge and activate commands must be separated on the command bus by at least a TRP amount of time. Now I'll describe the key mechanism of our high-throughput TRNG. We observe that a valid sequence of DRAM commands can activate 4 consecutive rows in quick succession in real DRAM chips. We call this phenomenon quadruple activation. To perform a quadruple activation operation or a QUAC operation, we first send an activate command, then we send a pre-charge command that violates the TRAS timing parameters. Instead of using the default 35 nanoseconds, we wait for less than 3 nanoseconds before sending the pre-charge command. We follow this up with another activate command, and this time we violate the TRP timing parameter. In doing so, we're able to open 4 DRAM nodes with just 2 activate commands. We identify 2 characteristics of QUAC operations. First, QUAC can only activate the set of 4 rows whose addresses differ only in their 2 least significant bits. And there's an example here that will hopefully clarify this. The diagram here shows the organization of a set of rows in a subarray at a high level. And QUAC can only activate the set of rows with the same color in this diagram. These rows can be rows 1 through 3 or rows 4 through 7. But QUAC cannot activate any set of rows that are different in color. Second, QUAC must activate the 2 rows with addresses that have their 2 least significant bits inverted. Here we use the same color to highlight the least significant 2 bits in row addresses that can be targeted by QUAC operations, activate commands to perform QUAC operations. When the first activate targets row 0 and the second activate targets row 3, we observe valid QUAC operations as the least significant 2 bits of these 2 addresses are inverted. Similarly, when the first activate targets row 1 or row 2 and the second activate targets row 1, we observe valid QUAC operations. We conducted experiments using our DRAM testing infrastructure, which I will talk about in the upcoming slides. and observe valid QUAC behavior on 136 real DDR4 chips. To explain how QUAC might be supported in current DRAM devices, we develop a hypothesis. And this hypothesis is based on the use of hierarchical word line schemes. These schemes are adopted in current DRAM architectures that have high density and high performance requirements, simply because they enable high density and low latency DRAM operation. In the hierarchical word line scheme, a master word line potentially drives multiple local word lines. And we will look at an expanded view of a DRAM mat to understand better. So the master word line drivers attached to either side of a DRAM mat drive the master word lines, and local word line drivers drive the local word lines that enable the access transistors in DRAM cells. These local word line drivers are enabled with a combination of the master word line and a certain control signal, which we denote as S0, S1, S2, and S3 in this figure. And now we will look at how the DRAM row decoder might be setting these control signals to enable QUAC in real DRAM chips. Our hypothetical decoder operates on the least significant 2 bits of the row address signal to set the control signals that drive the local word lines. The decoder logically operates in 2 steps. First, it pre-decodes the least significant 2 bits of the row address to form intermediate signals, and then it combines the intermediate signals to drive the control signals on the right. The decoder outputs, the pre-decoder outputs the least significant 2 row address bits along with their inverses and latches these signals. And the row decoder combines the intermediate signals using 2 input AND gates. We'll now see how an pre-charge activate command sequence that we use to perform QUAC operations enable all 4 word lines in this figure. We first issue an activate command to row 0, which sets the latches that drive A0 bar and A1 bar. This in turn enables the S0 signal, which is set by the bitwise AND gate that operates on A0 bar and A1 bar. The AND gates that drive S1 and S2 have partially set inputs. However, since A0 and A1 are not yet enabled, S1 and S2 are not driving the local word lines. With the execution of the first activate command, the decoder drives a single local word line. Following the first activate command, we send a pre-charge command while greatly violating the TRS parameter. And the pre-charge command cannot disable these 2 latches because there is not enough time due to violated TRS. We then quickly send another activate command as we greatly violate the TRP timing parameter, this time to row 3. And this interrupts the pre-charge process, and the latches that drive A0 bar and A1 bar remain enabled. Then the least significant 2 bits of the address are set to 1. And this enables the latches that drive A0 and A1. Since all intermediate signals are driven at this point, all bitwise AND combinations of these signals are also enabled. And with the execution of the second activate command, the remaining 3 word lines S1, S2, and S3 are enabled. This results in quadruple activation as all 4 word lines become enabled. Next, I'll describe how we develop QUAC-TRNG based on QUAC operations. First, we will see how we generate random values in DRAM sense amplifiers using quadruple activation. I will describe this over an example. This diagram depicts a set of DRAM cells on the same bit line and on 4 simultaneously activated rows. Initially, the even address rows are initialized with logic 1 values, and odd address rows are initialized with logic 0 values. The bit line and the bit line bar is set to half VDD, and the figure on the right depicts the difference in voltage between the 2 sense amplifier terminals over time. The gray dashed lines depict the reliable sensing thresholds that the bit line voltage must exceed for the sense amplifier to correctly amplify the value on the bit line. Since bit line and bit line
Hello? Can anyone hear me?
Yes,
Yes,
I can hear you. I
yes.
was checking my internet.
Okay, I think Ataberk has dropped off.
Yes.
Maybe someone can try to reach him, right?
Hello.
Is that Ataberk?
Hello. My electricity went off, and I have a really poor connection at this point. So it's a miracle you can hear me at this point.
Okay.
I'm sorry for this. It's like an infrastructure issue, I guess. I don't know what to do.
Okay. It's interesting we can hear you though.
Yeah, I connected using my mobile network, but this is not enough for me to present.
Okay.
Yeah, without any interruptions, I think.
Okay, interesting.
Okay,
Yeah,
electricity is back on.
Uh-huh.
I'm not sure if it's gonna go back, like go off again. I can continue now.
Yeah, I think you can continue, and let's see.
Yeah, in 2 to 3 minutes, I'll be able to share my screen.
Okay. Yeah, maybe we can take a quick break until Ataberk comes back up.
Yeah. Can you make me a co-host again, because I can't share my screen. Okay. Can you see the correct slide?
Yes.
Yep.
I think you got dropped off somewhere here, right?
Yeah. So I'll continue by describing this figure on the right again.
Sounds good.
Okay. So yeah, this is the figure. The figure is essentially showing the difference in bitline, sense amplifier terminals over time, and the gray dashed lines here depict the reliable sensing thresholds for the bitline voltage for the sense amplifiers to correctly amplify the voltage on the bitline. And since bitline and bitline bar are set to half VDD, the difference is initially 0. We start by sending an activate command to row 0, and this enables the word line, and consequently the DRAM cell on row 0 shares its charge with the bitline. Raising bitline, this results in the bitline voltage to raise slightly towards VDD. Next, we send a precharge command, quickly followed by another activate command to row 3. The second activate command enables the remaining 3 rows and keeps the first row open as it interrupts the precharge process. The sense amplifier is enabled soon after the second activate command. However, since the deviation on the bitline voltage does not exceed the reliable sensing threshold, the sense amplifier amplifies the value on the bit line randomly due to noise originating from random physical processes, such as thermal noise. And the bit line voltage will be amplified towards either VDD or minus VDD. We exploit this behavior and develop a high throughput true random number generator that leverages the random values generated on the sense amplifiers following QUAC operations. We will look at an example on how QUAC-TRNG exploits the high bit level parallelism in DRAM arrays to generate random numbers at high throughput. Here's a set of 4 consecutive DRAM rows, which we refer to as a DRAM segment. The QUAC-TRNG generates random values on the sense amplifiers in 4 steps. First, it initializes the DRAM segment using a predefined data pattern. In this example, we will fill the odd address rows with all zeros and even address rows with all ones. Second, it performs a QUAC operation to generate random values on DRAM sense amplifiers. At step 3, QUAC the random values on the sense amplifiers to the memory controller. And to do that, based on a one-time characterization effort, which I will describe in the next slides, it partitions the data on the sense amplifiers into arbitrarily sized blocks. Each block has a 256 bits of Shannon entropy. It reads each of these blocks to the memory controller and uses the SHA-256 hash function to post-process each block and finally output a 256-bit true random number. So QUAC-TRNG generates a 256-bit true random number for every one of these blocks it reads. Now I will present our evaluation of QUAC-TRNG's randomness characteristics, its quality, and its throughput. We conduct our characterization study on a 136 real DDR4 chips from SK Hynix to both understand the randomness characteristics of the results of QUAC operations and to evaluate QUAC-TRNG. We use a modified version of SoftMC, which is a DDR4 memory testing platform that lets us issue arbitrary DDR4 command sequences with any set of timing parameters to DRAM modules. And we use rubber heaters and a temperature controller to maintain the temperature of DRAM chips during our experiments. We use Shannon Entropy as a measure of randomness in bit streams generated using QUAC operations. So Shannon Entropy is calculated according to this, using this formula, and it can be interpreted as the effective number of random bits in a bit stream. To calculate this, the probability values in this formula, we simplify the proportion of logic 1 values and logic 0 values in the bit streams we test. And to calculate the Shannon entropy for each bit line, we repeatedly perform QUAC operations and read the sense amplifiers 1,000 times. The intuition behind this analysis is we expect a bit stream full of repeating values, such as all ones, to have 0 Shannon entropy, and a bit stream with an equal amount of ones and zeros to have Shannon entropy of 1. We conduct a characterization study at 50 degrees Celsius using nominal DDR4 voltage. And in our study, we collect 1,000 bit streams from each bit line in 8,000 DRAM segments using 16 different 4-bit data patterns, where each bit in the data pattern corresponds to the binary value we use to initialize all cells in a DRAM row. For example, the 4 ones data pattern initializes all 4 rows with all ones, and the 1000 data pattern initializes the first row with all ones and the other 3 rows with all zeros. We look at the cache block entropy to understand the effect of data patterns on the entropy resulting from QUAC operations. And we calculate the entropy of each cache block as the sum of the entropy of all bit lines in that cache block in every segment we test. Based on cache block entropy, we define 2 additional metrics. The average cache block entropy is the average entropy of each cache block in a DRAM module, and the maximum cache block entropy is the greatest cache block entropy we observe in a DRAM module. So on this plot, we display the cache block entropy on the y-axis and data patterns on the x-axis. The blue bars show the average cache block entropy, and the red bars show the maximum cache block entropy. And these values are averaged across all modules we test. The error bars indicate the maximum and the minimum values, where the upper tick indicates essentially the maximum value and the lower tick indicates the minimum value we observe across all modules. And note that the maximum possible value for cache block entropy is 512 because there are 512 bits in a cache block. We observe that the entropy varies with data pattern. We also exclude the other 8 data patterns that cannot generate significant amounts of entropy and in cache blocks from this figure. And we observe that the 0111 data pattern results in highest average entropy across all modules. Since the first row is activated slightly earlier than the other 3 rows, we hypothesize that when the simultaneously activated 3 rows are initialized with the inverse value of the first row's data, the bitline voltage cannot exceed the reliable sensing threshold in most sense amplifiers and result in random values on a larger majority of the sense amplifiers compared to other data patterns. To see if entropy changes according to the physical location of a DRAM segment, we look at each segment's entropy. We calculate the segment entropy similar to how we calculate cache block entropy. So we sum up all the bitline entropies in the segment. And the maximum possible segment entropy is 64,000 because there are 64,000 bits in a segment in the modules we test. We plot the segment entropy on the y-axis here over the segment ID on the x-axis. There are 3 curves on this figure. The red curve shows the average segment entropy across all 17 modules. And the error bars show the maximum and minimum values we observe across all modules. The dashed blue curve and the dotted black curve represent 2 main entropy variation trends that we observe across all modules. And we observe that the segment entropy behavior changes from module to module. And the entropy of the segment in the middle of the highlighted region, as you can see, behaves in an inverted way for the 2 modules M1 and M2. We also see that the entropy significantly increases near the end of the DRAM bank, around the 8,000 segment. To summarize, we make these takeaways from our evaluation. We see that the segment entropy changes according to both the data patterns we use in initializing DRAM segments and the physical location of the DRAM segment. And we attribute these to both systematic manufacturing process variation and design-induced variation-related effects, and you can see more details in the paper. We conduct 2 experiments to evaluate QUAC-TRNG's random number generation quality. First, we collect 1 megabit bit streams from each bit line in every segment from multiple DRAM modules using just QUAC operations. And we do this to show that QUAC operation can generate random values on sense amplifiers. Second, we collect 1 gigabit QUAC-TRNG bit streams using high entropy DRAM segments from multiple DRAM modules to assess the quality of QUAC-TRNG. We input the bit streams that we collect to the NIST statistical test suite in our evaluation. And here are the results of randomness tests for the 2 experiments on the 2 columns in this table. What these results show is that both QUAC and QUAC-TRNG bit streams generated by both QUAC and QUAC-TRNG pass all NIST tests, and therefore we can call QUAC and QUAC-TRNG high quality to random number generators. We estimate QUAC-TRNG's throughput for a DRAM module according to this formula. Here, SIB is the number of SHA input blocks in the highest entropy DRAM segment, and L is the latency of executing 1 QUAC-TRNG iteration in nanoseconds. We refer to a contiguous range of cache blocks with 256 bits of collective Shannon entropy in a DRAM segment as a SHA input block. And in this example, there are 4 arbitrarily sized SHA input blocks And we identify these blocks by rigorously characterizing DRAM modules for entropy resulting in QUAC operations. As an example, this figure plots the entropy of individual cache blocks in a high entropy DRAM segment. To identify a SHA input block, we find a set of contiguous cache blocks that have a total amount of 256 bits of entropy. We calculate L by tightly scheduling the DDR4 commands required to perform QUAC operations. And finally, we multiply by 256 as each QUAC-TRNG iteration outputs a 256-bit random number. For our throughput estimation, we evaluate 3 configurations for QUAC-TRNG. The first configuration uses a single DRAM bank. The second configuration exploits the bank group level parallelism in DDR4 to parallelize DRAM commands required to perform QUAC-TRNG iterations. And the third configuration uses row clone to bulk initialize DRAM segments row by row in DRAM. And it also exploits bank group level parallelism. We use the priorly proposed row clone operations to bulk copy data within a DRAM subarray to reduce the overhead of initialization. And we use activate, pre-charge activate commands with reduced timing parameters to perform row clone operations in real DRAM devices. We plot the average, maximum, and minimum throughput calculated for each configuration across all DRAM modules here. On average, QUAC-TRNG provides 3.44 gigabits per second to random number generation throughput. And its throughput is greatly improved by row clone as it significantly reduces the overhead of initializing DRAM rows. Finally, we compare QUAC-TRNG's throughput against 2 high throughput state-of-the-art DRAM-based TRNGs, DRANGE and Tolokter's mechanism. We calculate both DRANGE's and Tolokter's mechanism's throughput by tightly scheduling the DDR4 commands required to induce timing failures. And we augment both mechanisms by exploiting bank group level parallelism and by using row clone to bulk initialize DRAM rows whenever we can. And in our evaluation, we consider a base version for each mechanism where we evaluate them as they're proposed, and an enhanced version, which is a more fair version, where we characterize the entropy resulting from timing failures using 17 DRAM modules and use SHA-256 to optimize their throughput. And in our evaluation, we assume a system which has 4-channel DDR4 memory. And this plot shows the average throughput of timing failure-based mechanisms along with QUAC-TRNG. We project the throughput of QUAC-TRNG and prior work to various DDR4 data transfer rates displayed on the x-axis. We conclude that QUAC-TRNG outperforms the base version of the best prior DRAM-based TRNG by 15 times at a standard DDR4 transfer rate, and the optimized version of the best prior DRAM-based TRNG by 2 times at a potentially a future 12 gigatransfers data transfer rate. And you can check the paper to find more detailed information, including results on QUAC-TRNG's evaluation, quality evaluation using NIST randomness tests, throughput and latency comparison against 4 other DRAM TRNGs, discussion on how QUAC-TRNG can be integrated into a real system, the throughput provided by QUAC-TRNG while applications are concurrently running in the same system, the negligible area and memory costs of integrating QUAC-TRNG, and an analysis on the sensitivity of entropy resulting from QUAC operations to temperature and passing time. So I'll wrap up with a summary of our work. DRAM-based TRNGs can provide high throughput and low cost true random number generation to a wide range of systems. And the problem with prior DRAM-based TRNGs is that they're slow. And our goal in this work is to develop a high throughput and low latency TRNG that uses commodity DRAM devices. We observe that a sequence of DRAM commands can activate 4 DRAM rows in quick succession, which we refer to as quadruple activation. And our key idea in developing a high throughput DRAM-based TRNG is to use QUAC operations to generate random values on DRAM sense amplifiers. We evaluate QUAC-TRNG using real DDR4 chips and find that it achieves up to 5.4 gigabits per second throughput per DRAM channel, and it provides random numbers at low latency. we compare QUAC-TRNG against the state-of-the-art DRAM-based TRNGs and show that it outperforms the prior DRAM-based TRNGs. And finally, we evaluate QUAC-TRNG's quality using standard NIST randomness tests to show that it is a high quality to random number generator. And I am done with that. Thank you for listening, and I can take any questions now. And I'm sorry for the inconvenience of my electricity going off.
Okay, thanks, Ataberk. It's not, yeah, it's not your fault, so it's fine. Yeah, it was a very good talk, and I think this is a very nice work on true random number generation, of course. Any questions? Maybe everything was so clear that there's no need for any questions from anyone.
Yeah, maybe that, or they become distracted after the interruption and they cannot ask any questions now.
Yeah, this is a good opportunity to ask questions. Anybody attending the class, anybody who wants to maybe develop the new version of the DRAM true random number generators. Maybe I'll ask a question, Ataberk. So this clearly this work is very good at throughput. In terms of latency, how does it compare to other DRAM to random number generators?
Yeah, let me open the table we have for that. Okay, interesting. Wait, that was a black screen you saw right there, I think.
Yeah, you were making some things on it.
Yeah, I will get to that slide manually because I clicked on it and the carousel down below and it showed something weird. Okay, now this is, you can still see it, right? See the slides.
Yes.
Okay. So here we have the latency for generating 256-bit true random numbers using either QUAC-TRNG or using prior works. So we can categorize, I think, prior work under two main categories. One is high throughput, high throughput random number generators, and the others are rather low throughput. And the primary reason for that is that they take so much time to harness the entropy, the entropy coming from the random physical process to generate a random number. And you can see this behavior in the 4 other TRNGs that are based on either retention failures, DRAM startup values, or the randomness in DRAM command scheduling in a real system, basically. And these TRNGs are very slow in terms of both latency and throughput. For Talukder and DRange, it's QUAC-TRNG is comparable against their base versions. By comparable, I mean competitive and in terms of latency. And we have like 274 nanoseconds latency for QUAC-TRNG, where we have 250 and 260 for Talukder and DRange respectively. So that's one dimension. And the other is we have these buffers where we store random numbers in real devices. So it's already there in your contemporary processor, for example. We can utilize those buffers for DRAM TRNGs that have very high throughput and essentially hide the latency of generating random numbers. So latency becomes less of a problem when you have enough, let's say, enough resources to for buffering, and given that you're not continuously exhausting that buffer, I guess.
Yeah, that makes sense. Certainly buffering can help your latency, and the throughput that you get from the array itself determines how fast you can fill that buffer, right? Yeah. Okay, so in terms of latencies, basically it's comparable to the fastest prior work in terms of latency. So that's good.
So, yes.
I guess D-range is still faster because of the way it operates, right? Because it reduces the latencies.
Yes.
It violates the latency timing parameters and reduces the latency of access to generate random numbers.
Yeah, exactly. And when you parallelize it across like all 16 banks in this DDR4 module, you can achieve very high. You can get to that random number very easily, basically 256-bit random number. And also, these results we obtained using a 4-channel system based on a 4-channel system, and these numbers could change if you had a single channel. I guess that's some analysis we need to make also in the future, maybe. Because when you have 4 channels, you can immediately issue independently for, let's say, reduced latency accesses, and you will get the results almost immediately. Like this 36 nanoseconds for the range essentially comes from that. You can still, by utilizing multiple banks, reduce this latency, but not as much compared to when you have 4 channels available.
Yeah, that makes sense. That increases your per bit throughput, and as a result, you can construct the 256 bit number faster, right?
Yeah, exactly.
Okay, that's good. Yeah, I think it's really fascinating to figure out how to generate true random numbers using analog operational phenomena of storage and memory devices.
Yeah.
Maybe my other question to you. Clearly, this is important for processing in memory, even more so than existing systems, right? Because if you're doing processing inside memory, you would like to also have random number generation sources inside the memory.
Mm-hmm.
But is this the best you can do, or is there something else you can do that can do better inside DRAM, let's say? Or do you know the answer?
I don't know the full answer, but I can provide pointers. So this figure, or this one. So this is our hypothesis. Basically, we think that random values occur when the bit line voltage is below the reliable sensing threshold depicted in this figure as VTH. There is, let's say, prior work that backs this hypothesis up, and you can find this more details on that in the paper. Assuming this is the reason why we get random numbers, the obvious, I guess, let's say path, or the obvious let's say method that you can develop is to get a higher throughput, something that would keep the bit line voltage below these sensing thresholds, and then just amplify the voltage at that point. So if we could enable the sense amplifier without sending an activate command when the bit line is pre-charged, we could potentially generate random values on all bit lines or on all sense amplifiers in a row, and that will bring us to 64,000 random values per activation instead of what we get. Instead of what we get is around 2,000 on average in QUAC-TRNG bits in the full segment. So basically, you could potentially increase the throughput of QUAC-TRNG by 30-something folds if you can generate random values on all sense amplifiers with one activation. Yeah.
That's good food for future work, I think. Yeah. And this may be good synergistic with another paper that we examined, which is the codec paper, which was also published at ISCA 2021, which Lois presented some number of weeks ago, right?
Yeah, for sure.
Okay. Any other questions from anyone else? Otherwise, we should move on. Okay, thanks, Ataberk, for the nice presentation.
Yeah. Thanks.
So let's move on. Yeah, sure. Let's move on to another work. Christina, are you ready?
Yes, I'm ready.
Okay.
Hello.
Hello. maybe you can share your screen while I introduce you and what you're going to present.
Sure. Can I have the permissions to share?
Yeah, let's see. Can you do it now?
Yeah, I think so.
Okay, great. Okay, so the second work we're going to discuss was led by Christina, and it's efficient synchronization support for processing in memory, specifically near data processing architectures. Christina is going to introduce a technique called SynCron and look at the design space for synchronization and processing in memory architectures. Christina was a visiting PhD student at Safari, and she still continues to work with us. And she did this work partly while she was visiting us. And this work appeared at HPCA this year. And she is about to graduate with a PhD from National Technical University of Athens in Greece. And she continues to work on processing in memory. Actually, she has another work coming up on doing sparse matrix vector multiplication on near data processing architectures like UpMem. But maybe she can talk about that next year. Christina, please go ahead.
Okay, sure. Thank you for the introduction. As mentioned, in this talk, we will discuss about Synchron, and we'll discuss how synchronization among cores is implemented in near data processing architectures. And this is the agenda of this talk. We'll basically discuss three main points. First, we will see how synchronization is implemented in commercial architectures, like, for example, CPUs and GPUs. Then we will discuss if these synchronization approaches can be implemented in near data processing systems, if they are efficient, and what is different, what is new in near data processing systems in the context of synchronization. And finally, we will see the design of Synchron, which is an efficient synchronization mechanism targeting near data processing architectures. I will start with the motivation to enable efficient synchronization support in near data processing architectures. As we all know, recent studies have greatly renewed interest in near data processing architectures, or NDP. NDP architectures improve performance and energy efficiency of a computing system by moving computation closer to the data and reducing data movement. Therefore, NDP architectures are quite attractive for a wide range of application domains, including graph analytics, neural networks, bioinformatics, and many more application classes. At the same time, synchronization primitives like locks and barriers are widely used in those applications. For example, here you can see the single source shortest path algorithm, which needs lock primitives to protect shared data and ensure correctness in a multi-threaded context. Therefore, to fully leverage the benefits of near data processing architectures, an efficient synchronization mechanism among processing memory or near data processing cores is needed. However, supporting synchronization in near data processing system is challenging because NDP architectures lack shared caches among NDP cores of the system, and thereby synchronization would need to be implemented using main memory, however, with a great penalty in performance and energy. NDP systems also lack hardware cache coherent support, and the communication across the NDP units of the system is quite expensive. To this end, we designed Synchron. Synchron is the first end-to-end synchronization solution for near data processing architectures. We will extensively discuss Synchron, and we will show that Synchron provides high system performance, incurs very low hardware and area costs. It is very easy to use and generally supports a wide range of synchronization primitives targeting to cover a wide variety of emerging applications. Let's first examine the solution space for synchronization. Let's start with the baseline architecture that we assume. Typical NDP architectures support several NDP units connected to each other, with each unit comprising multiple NDP cores very close to main memory. These NDP architectures support high levels of parallelism, low memory access latency, and large aggregated memory bandwidth. In this paper, we have examined the synchronization problem in this baseline NDP architecture, and we find that there are three important characteristics that necessitate a new approach to support efficient synchronization in NDP systems. First, most NDP architectures lack shared caches. NDP architectures typically have a shallow cache hierarchy because NDP suited workloads do not benefit from deep cache hierarchy. They have poor locality, and therefore the communication could not be implemented using a low-cost shared level of cache memory between the cores. Second, typical NDP architectures lack hardware cache coherence protocols. Those protocols are typically not a good fit for near data processing architectures because they have very high area and traffic overhead. And finally, communication across the NDP units of the system is quite expensive, both in performance and energy. Based on these particular characteristics, we examine the solution space for synchronization, and we will see how prior synchronization approaches if they could be implemented in near data processing architectures and if they would be efficient in near data processing architectures. So synchronization means communication. Cores need to communicate with each other. Therefore, synchronization approaches are typically of two types, via a shared memory and via a message passing scheme. In the first case, cores coordinate between them via a consistent view of shared memory locations. They use atomic read-write operations or atomic read-modify-write operations in order to modify and change the values of shared memory location. And in this way, they communicate with each other, they exchange information, they coordinate, and they synchronize. The second approach is that cores can coordinate with each other via exchanging messages. Those messages can be implemented either in the software or in the hardware, and therefore they exchange information in order to reach an agreement. Both these approaches are implemented through various mechanisms that have been proposed in the literature, and many of them have been commercialized in real architectures. In commodity CPU systems, synchronization is implemented via the underlying hardware cache coherence protocol. The underlying hardware cache coherence protocols support atomic read-modify-write operations that can be used to synchronize the cores of the CPU architecture of the CPU system. However, most NDP architectures do not support conventional hardware cache coherence protocols due to their high area and traffic overheads, and therefore coherence-based synchronization primitives, which are typically used for synchronization in CPU systems, cannot be directly applied in near data processing systems. In GPUs and some massively parallel processing systems, synchronization is implemented via remote atomics. Remote atomics are dedicated hardware units which implement atomic read-modify-write operations. Those units are they are located in the memory hierarchy of the CPU system of the GPU system. For example, in GPUs they are very close to the shared level of cache memory, and using the atomics operations implemented in the remote atomics, the GPU cores can synchronize between them. However, remote atomics are oblivious to the non-uniformity of a system. And therefore, in NDP system, they would cause excessive, expensive traffic across the NDP units of the system with significant performance and energy overhead. And therefore, those approaches are not a very good fit for near data processing systems. Similarly, we have examined many prior works proposed in the literature which are oblivious to the non-uniformity of the system. And therefore, all these approaches do not constitute a good fit for near data processing architectures, which are typically non-uniform and distributed. And therefore, those approaches would cause excessive traffic across the NDP units of the system. Furthermore, prior hardware synchronization schemes proposed in the literature and targeting processor-centric systems like CPUs and GPUs are implementing, and they are built on the shared caches. However, NDP architectures do not include a shared level of cache memory, and therefore, if we try to implement these approaches in NDP systems, we would need to use main memory and implement synchronization via main memory. However, this would have a high hardware cost because we might need to modify the internal circuitry of DRAM. Therefore, these approaches are not a very good fit for NDP architectures. And finally, we have seen some recent NDP works, like the famous Tesseract paper, that propose software-based message passing schemes that can be applied in near data processing systems, and they implement synchronization via a message passing approach. These approaches include dedicated NDP cores to handle synchronization requests through the in-memory hierarchy. As we demonstrate in our evaluation, these schemes are still inefficient because they still use main memory to access synchronization variables, and they have a high latency cost. Therefore, overall, we find that prior schemes are not suitable or they are not very efficient for near data processing systems. And to this end, we designed a new synchronization scheme specifically targeting near data processing architectures, and we call this approach SynCron. SynCron is the first end-to-end synchronization solution for near data processing architecture and is built upon the message passing synchronization concept to avoid major issues via synchronization shared memory. Because if we implement synchronization via shared memory approach, we would need to use main memory, however, with a great penalty for performance and energy. SynCron eliminates the expensive traffic across NDP units of the system by implementing a hierarchical synchronization scheme. And finally, SynCron avoids using main memory to access synchronization variables by buffering all these variables to a specialized cache memory structure in order to minimize the latency cost. Let's now take a look on SynCron's design and how we address all issues related with synchronization in near data processing architectures. SynCron consists of 4 key techniques: hardware support for synchronization acceleration, direct buffering of synchronization variables, hierarchical message pass communication, and integrated hardware-only overflow management. First, we design low-cost hardware units, which are called synchronization engines, and they are located at each NDP unit of the system to coordinate synchronization among NDP cores. NDP cores communicate their request using 2 new ISA instructions, the RecSync and RecAsync, and the ISA instructions are used to assemble a message that is sent from an NDP core to the synchronization engine through the network and communicates necessary information from the software to the hardware. A synchronization engine includes the synchronization processing unit, which in turn includes a few registers, a small buffer, and a control logic, and is responsible to process, encode, and decode messages sent through the network. With the synchronization engines, we avoid the need for complex cache coherence protocols and expensive atomic operations, and also we provide very low hardware costs. Second, we add a specialized cache structure, which is called synchronization table, inside each synchronization engine to keep synchronization information and coordinate synchronization. When a synchronization engine receives a request from an NDP core for a synchronization variable, the synchronization processing unit processes the message and directly buffers the request in the synchronization table, keeping all the information needed for synchronization locally. With the direct buffering technique, we avoid costly memory access for synchronization and minimize the latency overhead. SynCron organizes the communication hierarchically. For a particular synchronization variable allocated in an NDP unit, the synchronization engine that is physically located at the same NDP unit with it is considered as the master synchronization engine. The master synchronization engine is responsible to globally coordinate synchronization for that specific variable. NDP cores send their synchronization request to their local synchronization engine located at the same NDP unit with them. In the next level of communication, local synchronization engines communicate with the master synchronization engine by sending aggregated messages on behalf of all its local cores through the narrow, expensive links that connect the NDP units of the system. The hierarchical communication is implemented via the corresponding hardware support inside the synchronization table. We include a local waiting list, which is a bit list, a queue list that includes 1 bit for each local PIM core within an NDP unit, and based on if the corresponding bit is set or reset, we keep track of the information if the particular NDP core has requested a particular synchronization variable. And also we include a global waiting list, which is used by the master synchronization engine to identify which synchronization engines of other NDP units have requested a particular synchronization variable. The proposed hierarchical communication minimizes expensive network traffic across NDP units of the system. Finally, when hardware synchronization resources are oversubscribed, Synchron uses main memory as a fallback solution. If the synchronization table of the master synchronization engine overflows, the master synchronization engine coordinates synchronization by issuing read or write requests to Synchron var in main memory. We include inside the synchronization engine a set of counters, which are called indexing counters, and they are indexed by the address of a synchronization variable to indicate if a specific variable is served using main memory or using the synchronization table. If the corresponding counter is larger than 0, it means that the synchronization variable is serviced using main memory because the synchronization table has been overflowed. To coordinate the overflow scenarios in a hierarchical manner, we have also designed specialized messages that is sent between the local and the master synchronization engine to indicate that the local synchronization table of a local synchronization engine has been overflowed, and therefore the master synchronization engine needs to keep all information needed in main memory using Synchron var. The proposed integrated hardware-only overflow management scheme effectively limits performance degradation in overflow scenarios and provides high program ease, since overflow scenarios are handled in a programmer-transparent manner. Synchron exposes to the user a high-level synchronization interface for the most widely used synchronization primitives, which are the log, barrier, semaphore, and condition variable primitives. However, in our analysis, we find that all different primitives they have a common principle. All synchronization primitives, they need to keep one queuing list to indicate which cores need to synchronize. And also they need to keep another information, which is a particular condition that needs to be satisfied in order to complete synchronization and move on the execution. Therefore, Synchron is designed to keep all this metadata and all this information in the proposed synchronization table. And therefore, Synchron is very easily can be easily extended to support other synchronization primitives like reader, writer logs, handshake, or monitors. I will briefly describe Synchron operation for the log primitive. So let's assume a scenario where all NDP cores on the system compete for the same log variable. They want to acquire the same log variable. First, NDP cores send local acquired messages to the local synchronization engines. The local synchronization engines decode those messages and set the corresponding bits in the local waiting list. They update the local waiting list to indicate that their local cores have requested a particular log variable. Then the local synchronization engine sends a message to the master synchronization engine to globally request the specific log variable. The master synchronization engine updates the global waiting list accordingly by sending the corresponding bit to indicate that the local synchronization engine of another NDP unit have requested the specific log variable. Then the master synchronization engine serves the local NDP cores, granting the log to the local NDP cores first, based on the local waiting list. And each time, whenever the service has been completed, it resets the corresponding bit in the local waiting list. Then, if there are no other local NDP requests, it will grant the log to the local synchronization engine of another NDP unit based on the global waiting list. The local synchronization engine of the other NDP unit serves the local NDP cores, serves all the requests based on the local waiting list, and each time it resets the corresponding bit in the local waiting list. When there are no other local requests from local NDP cores, meaning that the local waiting list is now empty, the synchronization engine releases the entry in the synchronization table and also releases the specific log variable at a global level by sending a global log release message to the master synchronization engine. Then the master synchronization engine resets the corresponding bit in the global waiting list. If there are no other requests, meaning that both the local and the global waiting lists are now empty, the master synchronization table, the master synchronization engine also releases the corresponding synchronization table entry. In a scenario where both the synchronization tables are fully occupied with other variables, the local synchronization engine needs to send a global overflow log acquire message to the master synchronization engine to indicate the overflow, and then the master synchronization engine coordinates synchronization using main memory. Both the local and the master synchronization engine increase the corresponding index encounters in the index encounter set to indicate that the specific log variable will be now served using main memory. We design a specialized structure, which is called SynCron bar, to keep all information needed to coordinate synchronization using main memory to handle overflow scenarios. As you can see, the fields in the SynCron bar are similar with the columns on the synchronization tables because we need to keep the same information. We have again a waiting list, and here we assume 2 NDP units, so we have 2 waiting lists, and we assume that each NDP unit has up to 16 NDP cores, so we have 16 bits in each waiting list. And we also need to keep some other information related with the condition to be met, to be satisfied in order to synchronize. So we have 2 more fields, the sync info and overflow info. So let's now take a look on the evaluation of this work and Synchron's benefits. We use SIMDRAM simulators, and we configure 4 NDP units, and we use the HBM memory technology provided by RowHammer. For Synchron design, we use Aladdin and Cacti, and we simulate the worst case scenario to handle a message, which is a barrier which relates with the barrier primitives, and we simulate it using 12 cycles. And we use a small synchronization table and a small set of index counters which have like 1 cycle latency and 2 cycle latency respectively, using according to the Cacti tool. So our evaluation includes 3 classes of applications, and we include 9 different pointer changing workloads, pointer changing data structure, 6 graph applications, irregular graph application, and time series analysis application. And we use a wide variety of these workloads in order to cover many synchronization scenarios and synchronization conditions. So in our evaluation, we use both coarse-grained synchronization approaches and fine-grained synchronization approaches. In the former case, in coarse-grained scenario, we have one synchronization variable to protect a large amount of shared data. In a fine-grained scenario, which is basically used in order to increase parallelism inside the workload, we have multiple synchronization variables, and each of those synchronization variables protects a very small amount of shared data. And also in our evaluation, we use the term synchronization intensity to refer to the ratio of synchronization over the other computation of the workload. And as this ratio increases, this means that the synchronization affects more the total execution time, and the synchronization is more important. It has more overheads during runtime. So we compare Synchron with three schemes. First, Central is a message passing scheme proposed in the Tesseract paper, where we have one dedicated NDP core in one NDP unit of the system, and this core is a synchronization server that coordinates synchronization using main memory, basically using its own memory hierarchy, and it keeps all information needed to coordinate synchronization using a synchronization variable allocated in main memory. Then we compare it with Higher. Higher is a hierarchical message passing communication scheme where we have dedicated cores, one dedicated NDP core at each NDP unit. And those dedicated synchronization server cores coordinate synchronization via a hierarchical manner. And they keep all information needed to coordinate synchronization using synchronization variable allocated in main memory, using main memory. And finally, we also evaluate an ideal synchronization scheme with zero overhead for synchronization. First, we demonstrate the performance of all these four comparison points by using pointer chasing data structures. In this plot, we increase the number of NDP units of the system. Each NDP unit includes 15 NDP cores, so we increase the number of NDP cores in steps of 15. And we saw the throughput achieved by all of these four synchronization schemes. So in this scenario, in the stack, we have a coarse-grained synchronization approach, meaning that we have only one global lock that protects the whole stack. If we have only one synchronization variable, or we have a few synchronization variables, all the cores of the system highly compete for those few synchronization variables. So we have a high contention scenario. In high contented scenarios, we find that the hierarchical schemes provide high performance benefits, meaning that the Higher and Synchron provide high performance benefits because they minimize the expensive network traffic across the NDP units of the system. Then we have a hash table data structure with 1K element. This scenario has medium synchronization variables, therefore we have medium contention between the NDP cores. In medium contented scenarios, we find that hierarchical schemes perform better because of two reasons. First, they minimize the expensive network traffic across NDP units of the system. Second, hierarchical schemes increase the execution parallelism. As mentioned, in the hierarchical schemes, we have one dedicated NDP cores or one synchronization engine per NDP unit. So we have more engines or more cores that concurrently process multiple synchronization variables, and therefore we have higher execution parallel. And finally, we have a fine-grained linked list with 20K elements. It's a very large linked list, and we have one log variable for each node on the linked list. So we have a fine-grained approach in this workload. And if we have a very high number of synchronization variables, we have very low contention among NDP cores of the system, because NDP cores of the system might work on different parts and different elements of the data structure of the linked list, and therefore they don't highly compete for the same variables. In a low contented scenario, we find that Synchron significantly outperforms prior schemes, Higher and Central, because it minimizes the latency overheads by directly buffering the synchronization variables in the proposed low-cost synchronization tables. Both in Central and Higher, the synchronization variables are accessed using main memory, so they frequently go to main memory and issue read and write requests to keep all the information needed in main memory. However, in Synchron, we don't go to the main memory, we don't use main memory, we keep all information needed in the proposed synchronization table, and this happens for a very high number of variables during the runtime. And this is why we get this amount of performance. And as you can see here, whenever we go from a coarse-grained approach to a fine-grained synchronization approach, meaning that we increase the number of synchronization variables in the workload, we find that synchronous benefits over higher increase because we avoid an even higher number of synchronization variables to be accessed via main memory. All these synchronization variables are now accessed using the low-cost synchronization table. Therefore, we conclude that in many different contention scenarios, even with low, medium, or high contention, Synchron provides the best performance and achieves very high throughput. Then we evaluate these four approaches using real-world applications, which include graph processing kernels like BFS, PageRank, and also we evaluate in a time series analysis workload. All these data applications have a high number of variables. They have fine-grained synchronization. They are implemented using the fine-grained synchronization approach, and therefore we have low contention. And we find that in all these scenarios, Synchron significantly outperforms both central and higher. And we also observe that the time series analysis is a synchronization-intensive application because the ratio of synchronization over the other computation of the workload is high. In synchronization-intensive applications, Synchron even further outperforms prior message passing schemes. Our synchronization portion is higher in the total execution time. And overall, we found that Synchron outperforms the prior best performing scheme by 1.23 times, and also comes within 9.5% of the performance of an ideal zero overhead synchronization scheme. And we conclude that Synchron performs best across all real applications. So in this figure, we demonstrate the system energy achieved for cache, network, and memory in all these real applications. We find that Synchron provides high energy reduction over prior message passing schemes because due to its hierarchical design, it minimizes the network traffic and therefore reduces the energy consumed inside the network. And also, thanks to its direct buffering capability, it minimizes the memory energy because it avoids using memory for synchronization. Therefore, it provides high energy benefits. And also, we find that the energy overhead over an ideal synchronization scheme is only 6.2%. Overall, we conclude that Synchron significantly reduces system energy consumption in real applications. In this figure, we compare all synchronization schemes varying the memory technology. We use HBM, HMC, and DDR4 memory technology. And we found that Synchron is independent on the memory technology used, and its performance only slightly varies over ideal across the different memory technologies. And also, we find that if the memory access latency is higher, Synchron's benefits over the prior message passing schemes, over central and higher, are even more important because we avoid accessing main memory, and the main memory has even higher latency access costs. So we provide even further performance benefits, even higher performance benefits. And overall, we find that Synchron is orthogonal to the memory technology used. And finally, we calculate the hardware cost of the proposed synchronization engine using Atai analogy. And we find that even with a larger technology node, the synchronization engine has much lower hardware costs, much lower area and power costs compared to a general purpose in order ARM Cortex-A7 core. Therefore, we conclude that our proposed hardware synchronization unit has very low area and power overheads to be integrated into the compute die of an NDP unit. We have evaluated many different sensitivity studies in our papers, including various data placement techniques, various transfer latencies on the links across the NDP units. We also evaluate the overflow management cost of our proposed overflow management scheme, and we also evaluate various sizes for the synchronization table. In this talk, I didn't manage to cover all these sensitivity studies, so we encourage you to read our HPCA 2021 paper. The key takeaway of all these studies is that Synchron is still effective across a wide variety of different configurations. In conclusion, synchronization is a major system challenge to retain all performance and energy benefits that near data processing systems provide. However, prior synchronization approaches designed for processor catering CPU or GPU systems are not suitable or efficient for near data processing systems. To this end, we introduced SynCron, the first end-to-end synchronization solution for near data processing architectures. SynCron consists of 4 key techniques: hardware support for synchronization acceleration to avoid the need for complex cache coherence protocols and expensive atomic operations, direct buffering of synchronization variables to avoid using main memory for synchronization and minimize the latency overheads, hierarchical message passing communication to minimize the expensive network traffic across the NDP units of the system and design a scheme which is aware of the non-uniformity of the underlying hardware platform. And finally, an integrated hardware-only overflow management scheme to avoid costly fallback solutions in overflow scenarios and provide high program ease. Our evaluation results show that Synchron approaches the performance and energy of an ideal scheme with zero overhead for synchronization. Therefore, we conclude that Synchron is highly efficient, low cost, easy to use, and generally supports many synchronization primitives to enable the widespread use and adoption of near data processing. And this concludes my talk and my presentation. I'm happy to take questions.
Thanks, Christina, for the comprehensive and nice talk and the solid work. Any questions from anyone? I guess people are silent today because we didn't have this in person. In person, we normally have a lot of questions. And also today is an unfortunate day. Clearly, it's very close to the holidays.
Yeah, that's true.
But feel free to ask questions. I think there's one question on Zoom. Maybe I'll read it. Maybe Theo is not able to speak. Did you quantify how often overflow occurred in your evaluations?
Yes, actually, we have designed our synchronization table in order to have enough entries and not to overflow very frequently. So imagine that there is an upper bound. As you can imagine that the upper bound is more or less the number of NDP cores that we have. Assuming that concurrently, all the NDP cores want to access at least 1 or 2 synchronization variables, and we have designed this our proposed synchronization table in this way. In the war scenario, you have like all the NDP cores of the system to concurrently access at least 2 or 3 synchronization variables each core. So there is an upper bound there, and if you design the synchronization table to satisfy this upper bound, you don't frequently overflow. So we include 256 entries, and we find that there are some fine-grained workloads that we overflow, but the overflow scenarios are like the percentage of the overflow that we have is more or less 2%. And of course, we have some performance degradation in those scenarios. However, in our paper, we compare with prior overflow schemes that have been proposed in the literature, and we saw that our proposed overflow scheme performs the lowest performance degradation compared to prior schemes.
Okay, that was a good question, and I think a good answer also. Overflow is clearly one of the reasons why you're there's a distance between the ideal mechanism and Synchron, right? Can you describe what are the other reasons of the discrepancy? There's still some headroom to reach ideal, of course.
Yes. So there is a trade-off there, because if you design the synchronization table to be very, very large, and you never overflow, the cost on the synchronization table is higher because you have a higher on-chip cache memory that you need to access, and the latency is higher. If you design the synchronization table to be small enough in order to have a very low cost, latency cost, you overflow very frequently and you need to go to main memory. So you have to tune this somehow. And the performance difference that we have compared to the ideal scheme is due to the fact that sometimes we might need to go to main memory, and we also have some latency. Still, we have some latency in our simulator. We do have some latency whenever we access the synchronization table. The ideal has like zero latency, zero overhead, never access nothing. Actually, it's an ideal scheme that we use. So we have some difference. And yeah, actually, that would be a very, very good study to have like a sensitivity study, and we compare the size of the synchronization table and the overflow that we have, and see the performance degradation and this trade-off.
Yeah, that makes sense. But ideal may be very difficult to reach, as you said, because it assumes zero latency synchronization,
yes.
and I think whatever you implement will have some latency.
Exactly.
Even if you don't overflow in the end to access the tables, you will have some latency.
Yes, exactly. This we include this in our evaluation just to show the upper bound and the ideal scenario, but we will never be able to reach that.
Okay, there's another question. I think I don't know if you can read it, but I'll read it for the benefit of others. Would it be possible to eliminate overflowing to main memory and just block when an overflow occurs, or would that lead to deadlocks?
Oh, that's also a very good question. Let me think about that. Yeah, I think that you need some kind of policy there, because whenever overflow occurs, it will also if you overflow in only one log variable, you will not have a deadlock. But if you overflow like in two variables, and those variables are related with the same critical section, they are competitive. So in that scenarios, if you block both of them, you will have a deadlock. I believe that you will have a deadlock, yes. So you need somehow, we need to design the policy, and you need to find a way to block not competitive variables in case of overflow scenarios.
Okay, great. I think Theo is satisfied with your answer, so he thanks you. Okay, I mean, clearly this is an interesting topic. We can ask more questions, but maybe it's time to move on to the next talk since we have limited time. For those who are interested in learning more about Synchron, I recommend reading the paper. And we also have a longer Safari live seminar that Christina delivered, I think a couple of months ago or last month. I don't remember exactly. You can find it online.
I think it was in September, and you can find that online. And also you can always reach us, and we are very happy to discuss that topic. Okay, sounds great. Thank you very much, Christina. Thank you too. Thank you for the invitation. Yeah. Okay, let's move to our third talk. I think I will continue without taking a break so that we don't overflow the lecture time, let's say. But while I'm introducing Geraldo, who's our third speaker,
who is sharing his screen right now, and also his video. I think Geraldo is joining from Brazil. Is that correct, Geraldo?
Yes, I'm in Brazil. This is why I don't have a sweater on.
Yeah, we're very international today. Yeah, so Geraldo is going to talk about SIMDRAM, a framework for bit serial SIMD processing using DRAM, which builds on the Ambit and row clone works that we discussed. We also actually discussed SIMDRAM in processing using memory lectures, but we didn't go into a lot of detail. And this work essentially improves the operational capability of processing using DRAM systems by enabling complex operations, and also improves programmability by enabling a flow or end-to-end framework for implementing those complex operations inside memory controller with support from DRAM, of course. And those operations get exposed as instructions that can be embedded into the programs. So it actually combines a lot of the interesting ideas that we have discussed, but it's the first end-to-end framework for processing using DRAM. And this work was published at ASPLOS in 2021. And Geraldo is one of the co-first authors. And Geraldo continues to do like exciting work that builds on this actually. So feel free to ask him any tough questions on this topic. And Geraldo is a PhD student in Safari. He's originally from Brazil. That's why he's in Brazil right now visiting family during the holiday season. Okay, I think take it away, Geraldo.
Thanks for the introduction, Honor. Don't ask so tough questions in the Christmas spirit, but feel free to ask any question and stop me anytime. So as Honor said, this is the SIMDRAM framework, a bit serial SIMD processing using DRAM framework, which was published in 2021. And with no further ado, I'm going to give a briefly executive summary what this work is about. So this work is in the context of processing using memory frameworks that can perform book bitwise operations using properties of the DRAM cells specifically to do some particular computation. However, those prior work that propose these book bitwise computations limits the amount of applicability for such architectures because they only support a limit and specific numbers of operations in these prior works. They also lack some flexibility to support any given new operations that the user might require. And if in the case that the process using memory architecture would enable more or complex operations, they would require significant changes to the DRAM subarray, which is quite costly, and DRAM manufacturers are often not so happy to change that design at all. So the goal of this work was to design a process using DRAM framework that can pretty much solve those three problems that I just mentioned. So we want to efficiently implement complex operations in DRAM while providing minimal changes to the DRAM architecture and providing the flexibility to support new desired operations as required by the user or application. To this end, we designed SIMDRAM, which is our end-to-end processing using DRAM frameworks, which is going to provide the programming interface, the instruction set architecture, and the hardware support to efficiently do computations inside DRAM, any computation that you want, arbitrary operation, at the same time that you can use a massively parallel in DRAM SIMD substrate. We extensively evaluate SIMDRAM, and we saw that it provides up to 88 times, and it's not up to average 88 times and 5.8 times the throughput of baseline CPU and high-end GPU, and also 257 times and 31 times the energy efficiency of a CPU and the high-end GPU, sorry, for 16 in DRAM operations. And we also implement some real-world applications leveraging our frameworks, several of them from various domains, from neural networks, for example, or image processing. And we see again that SIMDRAM can provide 21 times and 2.1 times the performance of a GPU and GPU for those 7 real-world applications. So here's the outline for this talk. So first, I'm going to give some overview about processing using DRAM and illustrate the problem that we're tracking in this paper. Then I'm going to provide some quick background about DRAM and those prior works that I mentioned earlier. And then I'm going to illustrate our SIMDRAM framework, then our system integration, evaluations, and conclusions. So let's get started with processing using DRAM. So as you should know, at this point in the computer architecture class, data movement is a major bottleneck in today's systems, mostly because the CPU or the compute engine, whatever you have, a CPU, GPU, FPGA, whatever, is usually connected through main memory through some bandwidth limited, power hungry memory channel. And the whole problem here is the number of pins that you can integrate and how you design the interface between the compute units and the memory itself. It's quite costly to include more pins to provide more bandwidth, and this also increases the bandwidth consumption of that link itself. So prior works in our group from Amorali shows that more than 60% of the total system energy actually in many applications is spent on data movement. So this is to illustrate that this memory channel is one of the main bottlenecks for a variety of applications. To solve this problem, processing in memory has been proposed, not now, but like in the 70s is the first paper about processing memories. But right now it's gaining some traction again because the problem is becoming larger and larger because of the amount of data that applications are generating and consuming. And processing using memory pretty much moves the computation here in the red engines here to inside the main memory device itself. In DRAM, caches, we're using SRAM or non-volatile memories here. We are working with DRAM. And by doing that, we can reduce or completely eliminate the need to move data between processor engines and the main memory device itself. One subsection of one subclass of processing in memory applications is what we call processing using memory, or PUM, which is going to exploit the analog properties or principles of the memory device itself or the cell itself to perform computation. This enables the architecture to leverage the large internal bandwidth and parallelism available inside the memory arrays themselves, and also is pretty low cost, right? Because you are not adding any hardware or a minimal amount of hardware on top of your memory device itself. And prior works have shown that you can use those porous memory architectures or the process memory architecture concepts to implement book bitwise operations, as for example, simple logical operations as AND, or XOR, or some more but still limited complex operations like addition or multiplication. So before I enter with the problem itself, I'm going to give some quick background about DRAM and the processing using DRAM architectures that I just mentioned prior. So Ataberk gave an overview about DRAM, so I'm going to go through this quickly. So a DRAM model is composed of many DRAM chips, and each DRAM chip is composed of several DRAM banks, and each DRAM bank has many subarrays, which are a 2D array of many DRAM cells. So the 2D array of DRAM cells are horizontally connected through word lines and vertically connected to what we call bit lines. So the bit lines are connected to an array of sense amplifiers, which are called a row buffer. DRAM itself is composed of a storage capacitor, which stores data in DRAM as a charge in some charge level, and also an access transistor, which enables and disables the charge flows from the storage capacitor to the bit lines. So when we want to access DRAM, the memory controller issues three different operations: activate, read and write command, and upper charge. I'm going to quickly explain each one of them next. So to read the charge level stored in the storage capacitor, the memory controller issues activate command, or ACT here, and it works as follows. So prior to receiving the activate command, the bit lines are going to be held under a reference voltage, usually half of VDD. And once when the memory controller issues the activate command, the first thing that's going to happen is that the word line of the target row is going to be pulled up or going to be asserted, and which is going to connect the all the cells along the rows to their respective bit lines. Second, the storage capacitor shares charge with the corresponding bit lines. And third, the sense amplifier is enabled in order to amplify the deviation, the sense deviation, voltage deviation in the bit line itself. And finally, letting the value that was stored in the DRAM, the storage capacitor, in the sense amplifier itself. So after this deviation in sense, the capacitance level in the storage capacitor is restored to its initial state. And now the memory controller can start reading the the data or sending read and write commands to read the data that was latched in the sense amplifier. After all of this happens, so the memory controller issues as many read and write comments for that particular row as is needed by application. But after the reads are done and prior to issuing new operations to that same the same array to the array of we need to precharge or issue a precharge comments to pretty much disconnect to first lower the word line and disconnect the sense amplifier, and then precharge the bit line back to this original state of half VDD in order to prepare the operation to a new prepare this array to a new operation to another DRAM row. So prior works have shown that we can actually leverage this operation that I just showed, this DRAM operation that I have shown, to do in-DRAM row copies and in-DRAM computation. So this work that proposed in-DRAM row copy is called row clone, and was also covered in the computer architecture class. So I'm going to briefly talk about it. So let's say that we want to copy the data in source row A and source row B, and both rows are connected to the same bit line and the same sense amplifier. To do that, row clone proposed sequence of DRAM comments that can do these operations without the intervention of the CPU. And this comment is called activate precharge. So first we are going to activate the original row, which is going to copy the bit line is going to be pull up, and then in the end you're going to have the data of source A in the sense amplifier. Then, without disconnecting source A or precharging the bit line, we are going to activate the destination row B, which pretty much is going to manage to copy the data that was originally in the sense amplifier in the source row A back to destination row B, which then is going to overlap the original data that was stored in B and then copying the data in row A to row B. Finally, we issue a precharge comment again, pretty much to prepare the DRAM array for to a new DRAM operation. Following the same idea or similar idea, we can also do what is called a majority function between 3 DRAM rows. So let's say that we have 3 DRAM rows, row A, B, and C, and all of them are connected through the same bit line. So Ambit proposes to do what we call triple row activations of 3 rows, which are going to create the majority functions of the values of the charge values stored in those 3 DRAM rows. So what we do here is actually we activate the 3 rows at the same time. So we activate row A, B, and C at once. And then the sense amplifier, the bit line, is going to be pull up to the majority value that was stored between those 3 DRAM rows. Here in this example, the majority of row A, B, and C is going to be the majority of VDD, VDD, and 0, which is going to be pulled up to VDD. And the end of the majority operation, the result of the majority function is going to be stored at the same time on the 3 rows involved in the majority computation, and the data is going to be overwritten. And this is a quite important observation later on. After all of this is done, we issue a precharge comment again to prepare the DRAM array for new DRAM comments. So Ambit proposed this work, this triple row activation to do in majority operations in DRAM, and they showed or they proposed both basically to do majority AND operations or OR operations, because the majority of you can do AND operations using majority if you set one of the inputs to 0, and we can do OR operations using majority if we set one of the inputs to 1. Also, Ambit proposed some optimizations or some modifications on the DRAM subarray in order to do this triple row activation in an efficient way. So in the Ambit design, the 2D array that I showed before is going to be broke down into 3 different groups. So the first group is going to be the group of 16 designed rows, and those rows are going to be what we call bitwise rows, and they are going to be the ones that we are going to do those majority operations on. Then we are going to have 2 rows of pre-initialized values, 1 rows of ones and 1 rows with zeros, and these rows are going to be used to control the and other operations depending on the operations required by the user. And then we have the regular DRAM rows that are used to store programs or user data. Sorry, and then we are also going to change the row decoders in the DRAM. We are going to introduce this bitwise decoder. Sorry, that we can use with a single DRAM address. We can activate 3 rows at the same time, thus doing the triple row activation that we need to do the bitwise operations as proposing ambits. All of these modifications in DRAM employ less than 1% of area overhead on top of existing DRAM chips. So as I showed before, or as I said before, DRAM and other memory technologies are in the as PCM, for example, are capable of doing this computation using memory. However, they also have some shortcomings. So for example, as I showed, ambit, it only supports some basic operations as Boolean operations. There are some works that build on top of ambit to enable some other computations as addition, but it still is only some few basic operations that are enabled by those works, which are not going to be able to be applicable in a large variety of applications. Again, there is the fact that they only support basic operations leads to the fact that only also support limited set of operations, which is going to create a flexibility problems. And also, if you want to solve those 2 problems that I mentioned before, prior works does support more complex operations, but they require significant change to the DRAM array. So what they usually do, those prior works that I mentioned, they propose to include some cells in the system amplifier, like CMOS gates or some simple NOR or simple FUs units in order to do the computation. But then that is quite costly because the DRAM manufacturing process is quite a sensitive process to changes, in particular to the DRAM array itself. As I said, it's costly and creates error problems. So this leads to the fact that we need a framework in order to enable the general adoption of processing using memory. And this framework should enable efficient implementation of complex operations in DRAM while providing the flexibility to support new operations. Therefore, our goal is to propose this framework that is going to enables us to do any complex operations in DRAM as we need, and also avoid doing any major changes in DRAM architecture at all. So then I'm going to start to introduce our process using DRAM framework, which is called SIMDRAM. So the key ideas of SIMDRAM is to provide these end-to-end process using DRAM frameworks that can do the efficient computation of complex operations in DRAM, while provide the user the ability to implement any arbitrary operations as required. At the same time, we are going to enable the DRAM array to become an in-DRAM massively parallel SIMD substrate without basically changing anything in the DRAM architecture other than was changed already by ambit. So first, I'm going to start with the process using DRAM substrate that we are going to use. So SynCron builds on top of 2 key ideas or 2 techniques that have been exploited by prior works, but not combined to provide the framework that we need to enable the adoption process using DRAM. So those 2 techniques are first using vertical data layout in DRAM. So usually in your system, in your DRAM system, your data is laid out in a horizontal data layout. So all the bits of a word are stored in the same word line in the same row. However, this creates a problem. The problem of implementing complex operations, like for example, think about addition, is that if you want to do the addition of some operands, we need to propagate the carry while we're doing the computation. If you think about a RIP carry adder. So if all of the elements are stored in a horizontal or vertical layout, there is no path for us to propagate the carry between on one operand in the other operand doing the computation. So prior works have proposed to include some shifting interconnect network in the sense amplifier itself to enable this propagation of data across bit lines. However, this is extremely costly, as we show in our paper. However, by doing this, by implementing, by storing the data, the words in a vertical data layout, we don't need anymore to include the shifting network in the sense amplifier, because now all of the operands are stacked on top of each other in the same bit line. So we do have communication within the same bit line for a particular computation. Yeah, so this is what I was just talking about. And at the same time, now each one of those bit lines that you have in DRAM are going to become independently SIMD kind of lane, because they can do independent computations of the other bit lines, and this enables a massive parallelism inside the DRAM array itself. So the second thing that we are going to leverage is the use of majority-based computation. So as I said before, Ambit have proposed to do all of those book-bitwise operations using, but they limit themselves to AND and OR by using those control rows. Here we are going to remove that control row at all, and we are going to use one of the DRAM rows for the input also for the computation. The main idea of doing that, of enabling majority-based computation instead of AND or not-based computation, is that we are going to have higher performance and higher throughput. Mostly because since the amplifier is actually doing majority, we can leverage that to reduce the number of triple row activation that we need to do a particular computation. So for example here, we have the Boolean equation on the top to do the carry propagation, the carry out in a full adder, in a rip carry adder. So this operation is going to require at least 6 and the NOR operations, if I'm not mistaken. However, all of this computation here can be replaced by a single majority operations, which is going to reduce the latency to do the computation and does also improve the throughput. Now I'm going to talk about our framework itself, how we're going to use those 3 techniques in our DRAM processing using DRAM framework. So as I said, SynDRAM is an end-to-end framework that provides the user the ability to implement arbitrary operations in DRAM. And the framework is composed of mostly 3 steps, which I'm going to illustrate next. So the framework takes as input operations, a desired operation for the user in the form of AND or NOT type of logic. And then this input is put on the first step of the SynDRAM framework, which is going to generate the equivalent majority not logic version of the input circuitry. And then in the second step, we are going to take this majority representation of the operation, and we are going to generate the sequence of DRAM comments in activate and pre-chart comments in order to implement that operation in DRAM. And we're also going to provide going to perform some optimizations on top of the generated sequence of DRAM comments to improve the performance of that particular operation when it's executed in DRAM. We call this sequence of DRAM comments microprogram. The output of the second step is first a SIMDRAM microprogram, which is stored in DRAM. Again, the microprogram is just the sequence of DRAM operations that implements the original input that the user inputs. And also we are going to include a new SynDRAM instructions to the CPU ISA, so the user can interface with that particular, can have an interface to execute that particular operation in DRAM itself. Then we have the third step, which is going to be done during the execution of the application. And for that, the user are going to have, we're going to use the BBOP operations in its application. And this is going to trigger what we call the control unit, which is stored in the memory controller. And this control unit pretty much is going to be able to execute those series of DRAM operations in order to execute the operation that the user required, completely transparently from the user, other than the fact that the user needs to include the BB operations in the application itself. But the control flow of the operation itself is completely oblivious to the user. The users don't see activate and per-charge command at all. In the end, we are going to have the result of the operation stored in memory. So I'm going to go through each one of those steps in more detail. To start with the first step. So as I showed, it's quite trivial to convert end or implementation of a. We can simply replace any OR operation with a majority gate, which one of the inputs is 0, or we can do the same for our OR. We can replace our OR gate to a majority gate where one of the input is set to 1. This is exactly what empty does. However, if you simply do that, if you simply naively replace and then OR gates through majority gates in a circuitry, we are going to end up with not the most optimized version of the circuitry, which is going to increase the latency of the operation that we want to do. So the goal of the first step is actually to solve this problem. We want to reduce the number of majority gates that we are going to have when you do this conversion of AND circuitry to a majority and OR circuitry to a majority circuitry. So this input, as I said, we are going to first generate that naive transformation of taking the AND and OR gates and replacing each gate with the majority gate with zeros or ones accordingly, and then we call this the naive graph. And then we are going to leverage some grid optimization works provided by prior works in order to optimize this circuitry and reduce the number of majority gates. The end of this input, the end of this step, we are going to have the optimized majority not implementation of the desired operation. So here, as you can see, we went from four different gates to only one single majority gate, and both of those circuitries here are equivalent because of this grid optimization algorithm. I'm not going to go into details about those grid optimization algorithms themselves. We invite you to check the appendix of our paper or this prior works which proposes this algorithm was the one that proposed this algorithm. So after that, we move to the second step, which we are going to generate the DRAM sequence to implement that optimized majority circuitry that I showed before. So before that, we have some notation that we use in this work. And first is the first notation is a microprogram. As I said, the microprogram is a series of microarchitecture operations. Here we define as microarchitecture operations activate or pre-charge command that SIMDRAM is going to use to execute the SIMDRAM operations in DRAM itself. The goal of the second step is to generate this optimized microprogram, so we can do the operations in DRAM as we need. So the second step has two tasks, as we called it. The first task is actually allocating DRAM rows to operands, so we can map that circuitry that I showed before, that was in the form of some graph, into the DRAM rows that we are going to do the computations. And in the second step, we are going to generate the microprogram. And in the second step, we are also going to optimize the microprogram in order to reduce the number of operations that are required to do the computation. So first, let's start with the first task, which is allocate DRAM rows to operands. So the goal of this task one is to allocate DRAM rows to the input operands of each majority primitives in the majority not-based implementation of the operand. So when we are allocating DRAM rows to operands, SIMDRAM is going to take into account the two extra constraints that are specific to processes using DRAM, particular processes using DRAM using ambit as is the base here in this work. So first, the number of compute rows that we have in a subarray, in the DRAM subarray, is quite limited. Here is only have 16 address or 8 rows. 8 rows, I guess so. But anyway, the fact is that we have some limited numbers of compute rows that are assigned to do the computation. The second constraint is that when you perform the majority operation in DRAM, we are destructing, or we are overwritten the input rows with the value of the result value of the majority operation. So majority operations in DRAM has a destructured behavior. So, and this is also needs to take into account when you are allocating DRAM rows to operands. So based on these two issues, we present a new allocation algorithm, which is inspired by the linear scan register allocation algorithm. So our allocation algorithm takes as input the majority not implementation of the operation generated in step 1, and start by assigning the input of each majority logic primitive to the available compute rows, to the available compute rows, one at a time. Since the number of compute rows are limited, 3 in this example here, this step of this algorithm assigns only as many inputs to the compute rows as the number of compute rows that are not allocated yet to any operand. Next, we perform perform a triple activation, as I said, in the compute rows, computes the majority of, for example, here A, B, and carry in, which in fact is going to compute the carry out of the in this example majority gate here. This is also for a full other. Our allocation algorithm is going to take into account the advantage of this behavior, that of the structure behavior, and reuses these rows for rows to operand allocation in the next round of triple row activations, in the case that the value stored in these rows is a input for the next majority function. So if the cout here is the input for the addition of the next part of the additional computation, we are going to be we can reuse each one of those 3 DRAM rows for the next phase of the computation. So we don't need to allocate new rows for the following input for the operations. In our paper, we have a description of these algorithms in details. So again, I invite you if you have any questions about that, I invite you to check the paper. So next, we are going to look at the second step, which is finally generating the microprogram. So the task 2 here has 3 key parts. So the first part generates the initial microprogram by simply copying the 3 input operand from the data rows to the DRAM rows allocated in the task 1 using the row copy operations proposed as in row clone, followed by the pre-charge operations. Then after that, after all of the inputs have been allocated to all of the inputs have been copied to for the data rows to the compute rows, we can execute the majority operation by issuing a triple row activation to those 3 specific rows. Then we can, in this case here, in this example, we need to copy the output of the operand back to from the compute rows to the destination rows by issuing another row copy operation. So the result of this DRAM of this first phase of this task 2 is what we call our initial microprogram. So this initial microprogram does implement the computation as required by the user in DRAM. However, this is not optimized yet. We can further optimize this microprogram by proposing some optimizations. So these optimizations are going to leverage the structure of the process using the DRAM substrate that we are using. So the first optimization that we are going to propose is to first coalesce row copies that are targeting the same inputs and the same inputs to the same DRAM rows. So we can do that basically based on the instructions of the subarray that we have in DRAM. And the second optimization that we have is that we can merge a majority operation following row copy operation into a single triple row activation operation also. So after you apply these 2 optimizations, we have a more optimized microprogram, which has fewer activate pre-charge sequence than the initial microprogram. The only thing missing here is that this microprogram here is only doing the computation for a single bit. So this is only doing 1 bit adding partially adding operation. This is for the carry out again, but yeah, it's only doing for 1 bit, and we need to generalize these operations in order to do an n-bit computation. And this n can be whatever the user needs. So it can be 8 bits, 4 bits, 16 bits, 32 bits, depends on the word size used by the operations. So basically what we're going to do is to generate the n-bit version of this microprogram by introducing some control microprograms inside the microprogram itself. And these control microprograms, micro operations, sorry. These control micro operations are going to be executed by the control units that I'm going to show next. After all of this, we have the final optimized microprogram, which is going to be stored in the DRAM area for future use, and also we are going to include a new SynDRAM instruction called BBOP to the CPU ISA, so the user can interface with this particular microprogram. So finally, we have the memory controller, and which is stored in the control unit, which is stored in the memory controller. So SynDRAM is going to use a control unit in the memory controller, which is going to handle the execution of the microprogram at their execution time, transparently from the programmer. So to perform a SynDRAM operation, the programmer needs to include the BBOP operations to its application. Once the program starts to execute, this BBOP operation is going to be issued to the memory controller and then forward to the control unit. And then the control unit is going to decode. You can think about this as a simple kind of MIPS type of processor. It's quite simple. And so you're going to, the main 2 tasks of this simple processor kind of thing in the memory controller is to first load the microprogram corresponds to the DRAM operations. So to load the sequence of triple operations that BBOP operations is referring to, and then to issue the sequence of DRAM comments in the sequence of the microprogram to perform the in-DRAM operations, and also to loop the operation as many times as the user needs. So you can do the computations in a bit serial type of fashion. As I said, in the end, the result of the operation is going to be stored in the memory. So this is the SynDRAM framework. Again, if you have any questions, feel free to stop me at any time. So we also discussed in our paper some system integrations in order to facilitate some challenge of processing using DRAM and to enrich our framework. So this is all of the system integration that we track in the paper. So we have how to transpose data efficiently, how you can do the program interface, how you can handle page fault, edit, translation, coherence, and interrupts, how you can handle the fact that the stable rate size is limited, the security implications of all of this, and the limitations of framework. In this talk, I'm going to cover the first 2 points over here, starting with how to do, how we can efficiently transpose data. So as I said in the beginning of this talk, SynDRAM operates on vertically layout data. However, the system, other system components, the cache, the CPU, is going to operate in horizontal data that is layout in the horizontal data layout, in the horizontal way. Now we have the challenge how we can share data between the CPU, the SynDRAM engine, which is doing computation in a vertical data layout, and the CPU, which is doing computation in a horizontal data layout. To solve this problem, SynDRAM uses a specialized hardware unit, which is placed between the LS level cache and the memory controller, called the data transposition unit. The data transposition unit is going to transpose data from the horizontal to a vertical data layout and vice versa. The transposition unit is going to have some unit called some units. The first one is this object tracker, which is going to track memory spaces or objects, as we call them in the paper, that the SynDRAM operations are going to touch on. So the user marks when a particular piece of data is going to be executed by SynDRAM, by touch by SynDRAM, and what it's doing is actually inserting an entrance in this object tracker. So when doing the execution of the program, this object tracker is going to track when memory addresses from a SIMDRAM object, and in the case of that, when the object is in the path to be evicted from the caches, this is going to trigger the horizontal to vertical transpose engine in SIMDRAM, which is simply some sets of buffers that are connected in a specific way, that when you read from one way, you write in the other way in the transpose manner. It's just a bunch of wires. It's nothing fancy. And then we can issue the writes to the memory controller already in this vertical data layout. And the same thing happens in the other way, in the other path. So when the CPU reads some data that was in the SIMDRAM, that was computed by SIMDRAM, and the object tracker see that is a SIMDRAM object, we are also going to trigger the vertical to the horizontal, the transpose engine, which again is going to some buffers wired in a particular way, which when you read them in a vertical data layout, you are going to be able to write them in a horizontal data layout. We show in our paper this transpose unit has low impact on the throughput of SIMDRAM operations, and also has low area costs compared to a CPU, particularly when you compare it to the CPU die itself. So the second thing that I'm going to highlight here is our program interface. So we include 4 new SIMDRAM ISA extensions to the CPU ISA, and those are first the initialization instructions, which again are the ones that the user are going to use to tell this particular memory address is going to be a SIMDRAM object, and this is going to be used to trigger the transpose unit. And then we have different type of operations. We have SIMDRAM operations that are built on one single input, 2 inputs, or also the predication operation that is built on top of 3 inputs. So here I have some example codes of how you can use SIMDRAM in your program. So here I have a simple C code for vector add sub operations with predicted execution. So this is quite simple. It's a for loop that goes through 2 arrays, and then I check if there is some condition. I do a plus B. The condition is false. I do a minus B. And what we do to transform these codes to equivalent code using SIMDRAM operations is first we need to mark that array A, B, and C are going to be used as SIMDRAM objects, so we can trigger the object tracker in the transposition unit. And also we need to issue the BBOP operations for each one of those operations that we have. So here first we do the addition, then we do the subtraction, then we do the condition comparison, and finally we do the if and else operation, the predication operation. As you can see here, we can completely eliminate the for loop that you have over here, because the for loop is going to be tracked by the control unit itself. So yeah, so it's quite similar how you would actually program AVX engine, for example, if you want to use the vector units in Intel processors. So for all of the other things that we have in the paper, we invite you to check our paper. So finally, I'm going to briefly talk about our evaluations. I'm going to skim through it a little bit because I guess we have another talk. So for our methodology setup, we use the Gen 5 simulator, and we have 3 different baselines. So high-end CPU, a high-end GPU, and also you compare it against Mbits using also a vertical data layout, but only use AND and OR operation, not majority. So we use SIMDRAM using a DDR4 device, and we use SIMDRAM, we evaluate SIMDRAM using one single SIMDRAM bank, enable bank 4 and 16. And this is going to enable basically a different amount of in-DRAM parallelism for doing the computations. We also evaluate 16 complex operations in DRAM and also 7 real-world applications. Those real-world applications, goes from databases to machine learning to neural networks and graphics. So first, I'm going to show some the throughput of the 16 SIMDRAM operations compared to those three different baselines. So here I have the everything average because a lot of data. So we have the CPU, GPU, and Mbed, and in the y-axis we have the average normalized throughput, and the values are normalized to each one of those baselines. So as you can see, the throughput SIMDRAM throughput is up to 88 times compared to the CPU baseline, up to 5.8 times compared to the GPU baseline, and 31.6 times compared to the Mbed baseline. It's not so fair if we compare to the 1-bit line, so it's around 2 times because we don't use Mbed with also 16 banks. But anyway, so the fact here is that SIMDRAM can significantly outperform all of those three state-of-the-art baselines for a wide range of operations. We do the same analysis for energy analysis for all of those 16 operations also, and we can see that SIMDRAM can provide 257 times the energy efficiency in gigaops performance per watt for compared to the CPU, 31 times compared to the GPU, and 2.6 times compared to Mbed. And also here I have the plot for the average speed up across all of these 7 different real-world applications. And again, SIMDRAM can provide 21 times the performance on average across all of those 7 real-world applications compared to the CPU, up to 2.1 times compared to the GPU, and up to 17.5 times compared to Mbed. So we conclude that SIMDRAM efficiently and effectively can accelerate many common use real-world applications. So we have much more in our paper. We have reliability of doing triple activations in DRAM, the overheads of doing data movement inside the subarray, also and across different banks, the overhead of doing the transposition, the data transposition, the area overhead in comparison to a prior works that is similar here. It's called duality cache, but it's again targeting in cache computing. And all of that is in our paper. So I'm going to briefly conclude. So what we are in this work, we are proposing SIMDRAM, which is a process using DRAM framework, which it provides the user the program interface, the ISA, and the hardware support to efficiently implement complex operations in DRAM, and provides the user the ability to implement arbitrary operations as required. All of that while doing using a massively parallel in DRAM CD substrate. Our key results are that SIMDRAM provides pretty large performance improvements compared to CPU and GPU, and the same improvement is also seen for energy efficiency, and also SIMDRAM can largely outperform those baselines when we use real-world applications. So in conclusion, SIMDRAM is a processing using memory framework that can ease the adoption of processing using DRAM architectures and improve the performance and efficiency of processing using DRAM architectures. So thank you so much for your attention, and I'll be glad to take any questions. I think I went a little bit further my time, but.
Okay, I think it's okay. Thanks, Geraldo, for the nice and comprehensive talk and the nice paper also. And we look forward to seeing your future works, making processing and using DRAM, processing using memory much more adaptable, let's say, and programmable and efficient. Are there any questions from anyone? Feel free to speak up or write. Maybe I'll ask one question. In our lectures, we also covered issues like coherence in processing in memory. How does coherence work with SIMDRAM?
Yes, this is a good question. So there are 2 types of coherence that we need to think about. So coherence across different, if you have multiple banks that SIMDRAM are enabled, so coherence across those different banks, and also the coherence between the CPU and the GPU, the CPU and the SIMDRAM computation, part of the computation itself. So I'm going to start with the last one, the CPU and the GPU and the SIMDRAM. So over there, we employ the, I guess, the easiest coherence model that we can have. So the transposition unit, when it receives some some requests from when we see there some SynDRAM object is being evicted, it start issuing cache flushing operations, flushing operations to evict everything that is dirt from the particular memory address space or that particular SynDRAM array is going to touch later on. So based on, and since the process is quite serial, we don't enable multi-threading or anything like that. That is enough to enable the coherence between the CPU and the SynDRAM when you're doing the SynDRAM computation. It's costly, yes, it's quite costly. So because the flash operations is quite high latency, but we can overlap some of that computation, some of that latency with the SynDRAM operations. The other part is that in the case that we have some SynDRAM, multiple SynDRAM banks doing some different SynDRAM computations, and they need to synchronize or do some computation, we don't evaluate that in the paper, and we don't enable that particular type of multi-threading. In that case, we do have some short paragraph in the paper saying that we do need to have some synchronization primitives implemented in the control units in the memory controller in order to enable data coherence and critical section, all those type of things, and also probably we need to enable some bare coherence protocols in low cost protocols in the memory controller itself, in the control unit. But there is a problem that we are tackling in the future work of SynDRAM that hopefully I'm going to be able to talk on in the future.
Yeah, hopefully. I think it makes sense. I think these two different kinds are important to distinguish and also enable efficiently going into the future, especially if you want to do reduction operations, for example, across different banks. You will need to do that in some place, right? And memory control is one place. Or if you have 3D stacked memory, the logic layer is also in a place. But still, you can improve the efficiency of those operations, certainly.
Yes.
I think related to the first one, a coherence between the CPU and SIMDRAM capable memory, let's say. If you also have compute capable caches, then you can potentially distribute the operation that you're doing such that some of it is done in the caches and some of it is done in main memory, right? So there could be some interesting scheduling issues for operations such that they can be performed wherever data resides without flushing the data from caches, right?
That is an excellent idea, actually. We can, ideally, we should make all of those processing using memory type of, or processing memory substrates like in a holistic way, right? So each one of them can assist the drawbacks of the other. Yeah, but definitely, if you have some in-cache computing capabilities, they can also handle that for us. It's definitely a really nice thing to think about in future works.
Okay, sounds great.
Thanks
Any other questions?
I don't see any question in the chat yet. Yeah.
Okay, I mean, someone on YouTube says good presentation, but that's not a question, so.
Thanks.
That's a compliment. Okay. Okay, since we don't have a lot of time, I think thanks, Geraldo, and we will move to the next presentation. And next presenter is Gagandeep Singh. Gagan, can you share your screen?
Sure. I need the right.
I thought someone would give you the host permissions, but I'll do it. Yeah. Okay.
Yeah, got it.
Gagan will also talk about near data processing, but a different flavor of it. He's going to talk about some of the work that he has been doing, especially on climate modeling, accelerating climate modeling, using near data processing accelerators implemented in FPGAs on real FPGA systems that make use of high bandwidth memory. Gagan finished his PhD recently in April in 2021, and he joined, he's been a part of Safari for some time, of course, but he joined as a postdoc after finishing his PhD, and he's continuing on looking at near data processing, FPGA acceleration, etc. I think he will also briefly describe the work he has done similar to this work, but accelerating genome analysis on FPGAs that can do near data processing. Okay, Gagan, please take it over.
Yeah. Thank you very much, Onur, for the introduction. And thank you everyone for waiting till the last presentation. So I'll jump right in. So first we'll discuss about NERO, which is a near high bandwidth memory stencil accelerator for weather prediction modeling. This work was done during my PhD in collaboration with TU Eindhoven and IBM Research Zurich. This was published in FPL 2020 and also was nominated for the Best Paper Award. So first I'll give a high level summary of the talk. So the motivation for this work was that stencil computation is an essential part of weather prediction applications. But the problem is this, stencils are memory bound with the limited performance and high energy consumption on multi-core architectures. And so our goal in this work was to mitigate the performance bottleneck of compound weather stencils in an energy efficient way. So the contribution we did was NERO, which was the first near high bandwidth FPGA-based accelerator for representative kernels from a real world weather prediction application. We performed detailed roofline analysis to show that weather prediction kernels are constrained by DRAM bandwidth on a state-of-the-art CPU system. At that time, it was state-of-the-art, and now we have the next generation as well, but still these kernels are bounded by DRAM bandwidth. And we also performed data-centric caching with precision-optimized styling for heterogeneous memory hierarchy using URAM, BRAM, and HBM because these FPGAs provide all these different kinds of memories. We also perform scalability analysis for both DDR4 and HBM-based FPGA boards, and we provide various insights based on that. In our evaluation, we show NERO can outperform a 16-core IBM Power 9 system by 4.2 times and 8.3 times when we are running these two compound stencils. And also it reduces energy consumption massively, and we get really good gigaflops per watt for different stencil kernels. So what I'll do, first I'll go into the background of stencil to just give an understanding of how these stencil kernels are. So the stencil computation, what it does is it updates values in a multi-dimensional grid using a fixed pattern of grid points. For example, over here we have a 7.3D Jacobi stencil, which is quite frequently used in benchmarking stencil studies. And what this kernel does, it performs it accesses 7 elements in the memory to perform 6 additions and 2 multiplication at the same time. And this pattern is applied throughout the grid, a 3D grid. And stencil are widely used in high performance computing and various scientific applications, for example, fluid dynamics, image processing, atmospheric modeling, etc. And these stencils have these stencils are really cache unfriendly, especially these multi-dimensional stencils, because they have limited arithmetic intensity, as there is reuse only in the neighboring pixels. And moreover, these stencils have sparse or complex memory access patterns, especially for when we are doing a multi-dimensional grid. For example, on the left, I again show this Jacobi stencil, and if we map this stencil onto onto a 1D plane, so how the memory access pattern would look like the figure on the right. So what we would have to do is to update each grid point, we would have to access 7 input variables, which would be in the different memory locations. And from the figure, it's not really hard to predicate that if we don't really carefully design our caches, there will be a lot of cache misses because of the remote accesses to the array elements. And that could eventually stall the program to a great extent. And therefore, this complicates the efficient mapping on traditional CPU-based systems. Therefore, these stencils are they have a performance bottleneck. And if we look at stencil computation in real-world weather prediction application, so we use a case study of COSMO, which is the Consortium for Small-Scale Modeling. It's a weather prediction model, actually, which is being used in Switzerland by Meteoswiss. And the central part of COSMO model is called the dynamical core or DICORE. And this one has around 80 different stencils with different compute motifs. And they use 30 variables and 70 temporary arrays. And it's really massive amount of computation that happens using stencil patterns. On the right, there's a figure which shows a small section of the Cosmos CDAC, where the blue nodes contain like the complex composed stencils. And these complex stencils are found also in like different applications. And each of these stencils have like really different access patterns compared to the other ones. And however, like this horizontal diffusion and vertical advection are the two more representative kernels out of all the stencils, and they give you like the diversity of the complete stencils which are present in the complete model. So we look into like these two like stencils. And these stencils, like previously I showed you this Jacobi stencil, which is like really an elementary stencil. However, the stencil computation in these weather model is like really different, and it's like quite complex. To demonstrate the complexity, let's look into like this horizontal diffusion, which is like one of the kind of simplest kernels inside. So these, as I mentioned before, these kernels are like compound stencils, and they have like these compound in the sense we have like a couple of stencils which are like cascaded together, and we apply like these stencil throughout the grid. And also it's not like you have the results of one stencil, you feed it to the next, but also you need to access the input data. So it's like there are like a lot of interdependencies which happen throughout the stencil execution, and because of which we have like really complex access patterns. Like the picture below shows the composition of this horizontal diffusion stencil, which has like Laplacian and flux stencils, which are being applied on the input grid. If you see like there's like the black node is the input node, and the white ones are different stencils which are being applied on the input data. And the figure shows like each stencil inside horizontal diffusion has a different access pattern. And for instance, like if we have a single evaluation of a Laplacian stencil, we need to access the input array at like 5 different offsets, and it's like a 3D grid. And so they are like the accesses are happening in like on a 3D input grid that leads to like irregular memory accesses, and you often have like cache misses because of that. And so that's why these stencils have like really bad, they're really bad for the traditional CPU systems. And now we also perform to understand like how these complex stencils perform on state-of-the-art multi-core system, we perform like a roofline analysis. So the figure here shows like a roofline plot where the x-axis is the arithmetic intensity, which is flops per byte. And on the y-axis, we have the performance. So over here, we show the peak performance of IBM 16-core Power 9 socket CPU system, which was until last year like the state of the art, but now they have like Power 10 as well. But still, like we have the same pattern for these stencils on CPU-based systems. So over here, we show like the single thread performance of these two compound stencils from Cosmo, vertical advection in the blue and horizontal diffusion in the green. And after completely optimizing these kernels for the power system, we still see there's like 1 order of magnitude lower performance than what you can get from the peak performance of the CPU system. And this is because of the memory bandwidth bottleneck which we have on standard CPU-based systems. And you can't really use like software techniques to overcome these bottleneck. And therefore, these weather kernels are like DRAM bandwidth constrained. So like in this work, what we try to do is like we try to come up with like different hardware platform that we can use for implementing these weather prediction applications. So there's like, as we know, there are like wide range of platforms that are available, like from CPU to GPUs and FPGAs. And they all provide like a trade-off between flexibility and efficiency. In our work, we focus on FPGA-based heterogeneous systems because FPGAs provide like really like the flexibility to create like domain-specific memory hierarchy for these kind of applications where you don't really perform well on like the CPU systems. So that's why like when you create your domain-specific hierarchies, you can handle these irregular memory access patterns efficiently. And also, like now we have like so many different kinds of heterogeneous memories available in FPGAs with the introduction of high bandwidth memory. So it became like even more interesting to like implementing like things on the FPGA, so you can understand like the trade-offs between like applications and perform like a hardware software co-design. So in our like system, we had like an IBM Power 9 system, which is a server grade system, and which was connected via a copy to interface, which is like a cache coherent interface from IBM. And in our evaluation, we made use of like two different FPGA boards. The first was Alpha Data 987 board, which had like the state-of-the-art HBM memory. And the second one was IBM, we had like Alpha Data 9v3 board with DDR4 memory. So we tried to have like this design space of like different DRAM memories so that we can have a comparison of like how, like what are the benefits of HBM and how you can exploit those compared to a traditional DDR4 memory. Now I'll present like our key contribution, which is NERO. First, I'll talk about like the details of like how the architecture is and how the data flow sequence happens inside NERO. So first we have the weather data, which is stored in the host DRAM, which is based on the atmospheric model resolution grid. And like, as we know, like the FPGA has like limited resources, which you can use to like build your own accelerator. So what we propose in this work is to have like a 3D window-based grid transfer from the host DRAM to the FPGA, so that we don't really use all the resources on the FPGA, but rather than like we work on small portion of data. And this window represents the portion of the grid a processing element would process on the FPGA side. And we employ a double buffering technique between the CPU and the FPGA to hide the transfer latency between FPGA and CPU. And we configure like a buffer of like 32 cache lines, because that's the maximum between the AXI and between the CAPI2 and the FPGA, so that we can exploit the complete bandwidth of CAPI2 interface coming from the host side. And on the FPGA side, like once we have the data, we perform like an initial buffering of the transfer data, and then we map it onto the HBM memory. And this HBM memory is quite different than the memories which are available in terms of DDR4, because HBM has like multiple stacks, and each stack offers you like 16 pseudo memory channels. And so in total, you have like 32 such ports, which are available for you to exploit, and you can independently access all the ports the way you want. So it's like you have massive amount of bandwidth. So as a designer, like you have to think about like, how would you exploit such large amount of bandwidth to come up with like a balanced design when you're creating your accelerator, so you have like really large amount of parallelism. So that's what we tried to do. We studied those things over here and tried to do like, how can we exploit these large amount of number of ports which are available to us. So what we do is like we have like, so we place our processing elements, which are like the accelerator on the FPGA side, and we enable as many ports as the number of accelerators. So each accelerator has like independent access to the memory channel, so they are not bottlenecked by trying to like fight for the memory channel to fetch data. And then like we have like in our design, we have the stream converter logic, because the HBM has like each channel is 256-bit wide long, and our external memory, which external interface to the host system was 512 bits. So we tried to match this by like having a stream converter logic so that we operate on like bigger amount of data. And then we have like these stream splitter logic, because these weather kernels, they need like couple of variables, like couple of like atmospheric components like wind, pressure, velocity, etc. And then we had like, so all the data comes as a stream to the FPGA, and then we try to like split it into like different streams, which each stream represents like different components of the weather components. And then like, and once after we split this data, then there's like each of these data is being independently processed by the processing elements. And then we create a domain specific memory hierarchy using like the URAM and the BRAM memory. Like as I mentioned before, like the beauty of like now these FPGAs, like you have so much heterogeneity and you can exploit those and create the memories the way you would like to do that. So there's like a lot of like different ways you can create those, and we use like different reshaping techniques to configure the memory space so that we can parallelly access like different these memory elements for our different processing units. And we use a lot of like these partitioning of data and like various techniques which are known for like for the designers. On the processing side over here, I show like the vertical advection kernel because it's a bit more complex than horizontal diffusion. And the way it operates is like we have like a forward sweep and a backward sweep. So first you perform like a couple of computations on the input data. So you go in the forward direction and then you buffer those results in a FIFO. And using those results, then we perform a backward sweep on the complete data which was generated from the forward sweep. And these computation, like it's much more complex than horizontal diffusion, and it has like large amount of control flow as well. And yeah, like all these tasks which we do is like and once we are done with the processing of this data, we send the data back to the HBM channel, or like we also provide a switch if you don't want to store the data on the HBM memory, or if you want to offload directly to the host CPU system, you can do that. So we have like quite a bit of flexibility in our design of like how the data should be mapped. And the complete design works in a data flow manner. So everything is like in a pipeline fashion. So you get like a large amount of task level parallelism. And to support this architecture, we also build like an application framework, which is like, as I mentioned, like we have our host system, which offloads the processing onto the FPGA by using like over this copy-to interface, which is like this a coherent interface, and like our Cosmo API, which we build like a kind of a library which is there, which offloads the processing using an interrupt-based queuing mechanism. And this allows us to have like a minimum CPU usage during the FPGA operation. And so the CPU can keep on working on something else. Meanwhile, the FPGA is like trying to do the processing of like the offloaded workloads. And we use a Snap framework that allows for the seamless integration of your accelerator with the power system with the CPU. So everything is like available on GitHub. And we have like many more details in our paper about like how we implement our application framework. So I would really tell you to refer to the paper to understand like the application framework. And also we also propose the use of precision optimized tiling. So as I mentioned, like we offload a part of data from the host CPU to the FPGA, which is like in terms of the window sizes. And usually what we do is like as a programmer or as a developer, we always use like a manual with like a window size, for example, 8x8 or 16x16. But we see like there's like the window size is really critical when you do any processing on the FPGA, because you have limited amount of resources on the FPGA. So you would like to maximize those resources and performance. So what we do is like, instead of just offloading any like random, like manually designed window, we formulate the search of the best window size as a multi-objective auto-tuning problem. So what we do is like, we use like machine learning to understand like what would be the best window size, taking into account the precision of the data, because also we see if we have like different precision type, either we have like single precision or double precision, you get like different amount of window size that would be ideal for your execution. And that's why we use like machine learning, and we propose that to use while performing like these window-based optimizations. So over here, like I'll discuss briefly like the effect of this styling of like different window sizes. So for example, over here we have like auto-tuning results of like for vertical advection for a single processing element, where we have a resource utilization versus the performance. And if you see, like we have like completely like different trade-off, like a different number of like if we use like different window size, we get a different trade-off. And if we see like the auto tuning finds us like 64:2 as the best window size, rather than having like a window size of 8:8 or something. And that's how we show like these hand tuned results can be like really suboptimal compared to an auto tune, like where you're using like machine learning to come up with these kind of like the optimized window size. And we also do like half, and actually for half precision, the window size is a bit different. It's not the same one which you can use. So it's really good to do like auto tuning, taking into account the precision as well. So as I mentioned, like Pareto optimal size depends really on the data precision. And so we employ that as well in like while we are building our accelerator design. So I'll briefly go into the evaluation of like our results. Like we perform like both performance analysis and also energy efficiency. So first, if I discuss the single precision performance results, this plot is for vertical advection. And we have, as I mentioned, like in our evaluation, we evaluate both HBM-based FPGA and also the DDR4-based FPGAs. And we perform like in-depth scalability analysis of like how your performance scales when you have like more number of processing elements with the different number of channels, the processing channels. And if we see like we provide like a couple of observations. For example, like when you have like a single processing element, which is fetching data from the memory. So you get like higher performance from a DDR4 based memory than an HBM based memory, because DDR4 based memory has like a higher bit width compared to the HBM memory, which is almost double. So that's why we see like more performance when you're using like DDR4. But once you start scaling, we see like a linear like reduction in the runtime. And also like once you have like, for example, you have like four processing elements, but the DDR memory can't provide like a large number of channels, which HBM can provide. So we start seeing like a kind of a congestion which happens, because now different processing elements are kind of like fighting to use the same channel. So in that aspect, like HBM provides you like really great scaling capabilities, which are not possible using like the previously available memories. And also like we perform like similar studies for horizontal diffusion as well. And in there, like we saw like with using like our careful design and also using like different techniques, we were able to get like 4.2x and 8.3x faster performance than a complete Power 9 socket. And also we performed energy efficiency analysis for our design to understand like whether like we understand that like we can get like a lot of performance from like different channels, but also like we wanted to study like how this energy efficiency would be in terms of when we scale the number of channels. So for over here, again, we have a plot for vertical advection. And we have, again, for HBM based and DDR4 based designs. And like first, like we again made like a couple of observations. So the first observation was in line with the observation which we had when we performed the performance analysis, that like when we are using like only like one processing element, then you get better energy efficiency from DDR4 based design rather than HBM based design. But however, as we start increasing, we again see like the performance is like we're getting better energy efficiency from HBM based designs. But actually, after a while, it kind of saturates because especially for this vertical advection, because as I mentioned, it's a bit more complex and it has a lot of like control flow compared to horizontal diffusion. So in the end, like it's not super well suited to be accelerated on the FPGA, but in the end, we still get like better performance compared to CPU. But like the scaling is like in terms of energy efficiency because of like large amount of control flow, and also you're enabling a lot of HBM ports. That's why you get like, and the HBM ports consume a lot of power as well, depending on like what's your data rate and everything. But still, like it's like what we observe is like enabling many HBM ports might not always be the determining factor. So you really have to balance your design. You have to think about whether you're thinking about energy efficiency or performance. So like these are things like you have to take into account, and we provide like many more observations, like such kind of observations. So which helps like future designers to build up like an efficient accelerator. And similarly for horizontal diffusion, we showed like our energy efficiency analysis over here. We didn't see any degradation in the energy efficiency because like as I mentioned, it's like quite easy, not relatively easy to parallelize, and it's really well suited to be accelerated on FPGAs. And there have been like a lot of works which have been like now showing the benefits of horizontal diffusion on FPGA, and people have been following up on like trying to come up with like better accelerators for these. And so this is like one of the kernels which works really good with HPM, even in terms of energy efficiency. So yeah, in the end, like we get like really good results in terms of like compared to an like a CPU based system. And yeah, like so we provide like a lot of details about this in the paper. So I'll briefly summarize this work so we can like quickly jump into the other work as well, which builds up on like the things we learned from while building a NERO accelerator. So in summary, like stencil computation is an essential part of weather prediction application, and also in like many other like scientific applications. But the problem we have with these stencil computation is that they are memory bound with limited performance and have high energy consumption on multi-core architectures. So our goal in this work was to mitigate the performance bottleneck of compound weather kernels in an energy efficient way. So we contributed NERO, which was the first HPM-based FPGA accelerator for representative kernels from a real-world weather prediction application. So we were the first to study how HPM, a real-world like the commercially available FPGA with HPM is for like a real-world application. We also perform like digital roofline analysis to show like how these kernels are DRAM bandwidth bound on a CPU-based system. We perform data-centric caching with the precision optimized styling for heterogeneous memories by leveraging all the different types of memories available on FPGA and carefully designing our accelerator. And we also perform like scalability analysis for both DDR4 and HPM-based FPGA boards. And then we provide like various insights and how your accelerator would behave once you start building using HPM. And we also extrapolated not just to Stencil, but also like different application, how they will behave based on like our insights, which we gained. And in the end, like in the evaluation, we showed like we can outperform easily like the CPU-based system with like really good results. And also like in terms of energy efficiency, we can get like better energy efficiency if we are offloading this computation to an FPGA. And yeah, I would like, for more detail, I really invite you to read our FPL paper. And like based on like the insights we got from this work, like which we did in like in NERO, like recently we also published another work which is called FPGA-based near memory acceleration of modern data intensive applications. And it was published recently in like IEEE Micro. And what we did in this work was we took the lessons which we learned from NERO and we extended our work to a completely different domain of genome analysis. So it's really exciting for me as well, like because to understand how like we can accelerate like a completely different domain, especially in terms of in the times of COVID, like where we need like efficient techniques for like genome analysis and sequencing. So I'll give a really quick genome analysis overview. So, but I would like motivate you to read like many more papers which we have in our group on genome analysis to understand like in depth about like how these algorithms work and what are the problems. So in genome sequencing, until today, there's no machine that gives the complete sequence of a genome as an output. So what we have today is like sequencing machines that provides like small randomized sequences of the original DNA sequence. And these are called as reads. And since these reads do not have any information of the origin or the order of the reads, so they are like just randomized sequences of ACGT. And so then because of that, we have to go through a computationally intensive step, which is called read mapping. To understand like to get like the initial like complete sequence of genome. And we observed that like there have been like a couple of works which have shown this observation that sequencing machines are doing quite well right now compared to like the rest of the steps in the complete genome pipeline. For example, a sequencing machine can sequence 48 human genomes with a 30x coverage in about 2 days. However, now we are bottlenecked by the read mapping step. where we can process only one human genome in 32 CPU hours on a 48 core processor. So it's like really a big problem. And there have been like a lot of efforts to efficiently like overcome this bottleneck. So if you look into read mapping, there are like three main steps. First is like indexing, second is pre-alignment filtering, and the third is sequence alignment. And for each step, there are like many different kind of approaches which you can use. But in essence, like 60% of the time of read mapping is spent on the last step, which is like the dynamic programming step, because it's computationally quite intensive. And the past works have shown that there's like an overwhelming amount of candidate location that have really high dissimilarities with a read. So which means that we don't really need to do this step for each and every read. So we can get rid of a lot of reads and we don't really have to go through this step. So the point, like if you can do that, by how you can do that is by means of like having a good pre-alignment filtering step. So this second step, this pre-alignment filtering, it can get rid of a lot of these reads so that you don't have to go through the final step, and it really helps you end to end to increase your performance. And that's why like in this work, we looked into like how we can efficiently like design this pre-alignment filtering step for this HPM-based FPGA systems, where we perform like a software hardware code designed to come up like to have an efficient pre-alignment filtering. And the key, so what we did, we used this Sneaky Snake, which is a state-of-the-art pre-alignment filtering, which is from our group as well. And the key observation of, I'll give like super brief overview of like how this Sneaky Snake is, but I would really recommend you to read the paper to understand more about it. But the main observation of this Sneaky Snake is like the correct alignment is a sequence of non-overlapping long matches. And the key idea of this algorithm was to like use approximate edit distance calculation to make it like, which is quite similar to like single net routing problem in VLSI chip. So so how it looks is like, for example, we have a VLSI chip over here, and when we dissect the chip, we can find like there are like many components inside the chip, and the problem becomes like there's like a snake. So it's kind of a maze, and the snake wants to go from like one end to the other end, and it needs to find the shortest distance to go out from like one end to the other end. And that's why it's called, like, the algorithm is called Sneaky Snake, because it's trying to come up with like the sneakiest way to come out. And so that's how like this pre-alignment filtering has been like used as like a single net routing problem, where we build up a matrix of like these reads, and then we try to find like the shortest way to come out. So for more detail, I recommend you to read the paper. But once if we have a similar like roofline plot, which I showed you before, and if we try to map this pre-alignment filtering on this roofline plot, where we already have these two weather prediction application, we observe that this pre-alignment filtering is even more memory bound, and it performed really poorly on the CPU-based systems. So therefore, like, it becomes even more important to somehow like efficiently like accelerate this workload and these applications, so that like you can like accelerate the complete pipeline. So that's what, like, in this paper, we extended our work so that like we can overcome this memory bottleneck for these pre-alignment filtering. And also we extended like previous work which we did for like weather forecasting, with like having like more evaluation and like providing more insights about like how you can efficiently use these these state-of-the-art systems. So our goal was, again, like to mitigate the performance bottleneck of these like data-intensive applications using state-of-the-art FPGA-based HPM-based systems. So like we were using the same heterogeneous system we had, but now we also extended it with like two new interconnect technologies. Earlier we had just CAPI2 between the host system and the FPGA, but now we had like Open CAPI as well, which provides like double the amount of bandwidth. And also now, like earlier, we were using a single channel design where we were just fetching data from like one HBM channel, but now we also try to have like multi-channel design where we are fetching data from multiple HBM channels. So we have like extensive amount of evaluation for like these two data intensive application domains. And so we provide like result, like again, like performance analysis and also like energy efficiency analysis. And we show like we can like greatly accelerate our application if we use like these HBM based designs. And also like they can avoid, like as I discussed before as well, like these HBM based designs can avoid memory access congestions, which is typical of like DDR4 based FPGA designs. And we provide like many more results on energy efficiency analysis, and in the end we show like we can get up to like 100x better performance on if we go for like compared to CPU based systems. And we also open source our design for both for single channel and multi-channel designs. So I would recommend you to have a look on these. And in the end, like I would really encourage you to read both our papers, like IEEE micro and FPL papers. So yeah, thank you for listening to my talk. I went a bit over time, I think.
On time, 20 minutes later. Oh,
sorry.
Yeah, now I can hear me. You can hear me now, right?
Yeah.
Thank you, Gagan, for the high bandwidth talk, just like the high bandwidth memory that you've been taking advantage of. I think this is certainly very interesting research, especially accelerating two important data intensive applications. And hopefully there will be a lot more interesting research going into the future, combining reconfigurable logic, processing in memory, and heterogeneous architectures in different ways. I think we're already over time. It's good that some people stuck around, but none of this is required anyway. So it's for people's benefits. Any questions? Any burning questions I should ask now that you have Gagan on the line? Yeah, if not, then I think for the sake of time, we should probably end it here. This is also the end of our last lecture for computer architecture this year. So I hope everyone enjoyed the class, and people can watch all of these lectures for the future anyway. So hopefully it'll be a good reference for others to build on. Okay, I don't hear or see any other questions, so maybe we should just conclude the class here, and I hope we will see each other in some other class going into the future. Next semester, we have the digital design and computer architecture class, which is an undergraduate level class, and we will have a new edition of it, which will cover some of the ideas that we have discussed in this class as examples, but it's clearly a more basic class that people can attend and learn how computers work from the ground up, from the transistor level all the way to programming level. Okay, have a nice holiday season. Happy New Year to everyone. And we will see you in 2022. Take care. And thanks again, Gagan. And thanks again, everyone else who has presented in this last session. Bye-bye.